Do you hear me?
Yes, we hear you. We're just about to start now.
Okay, thank you.
So it's my pleasure to welcome you to the first session of the last day of Amplitudes 2022. And right now we're very pleased to have Alessandra Bonanno from the AEI in Potsdam and the University of Maryland, who will take us from scattering amplitudes all the way to gravitational wave observations. Alessandra, please begin.
Good morning, and I would like to start by thanking the organizers for giving me the opportunity to give these talks. I'm not sure I will really bring you from scattering amplitude to gravitational wave observations, but perhaps discuss what is needed to go there. Okay, so as you know, gravitational waves have become the new tool to explore the universe, and in order to infer astrophysical and cosmological information from the gravitational wave observations, detecting possible deviation from runs of the LIGO and Virgo and Kagra collaboration and future detectors in space and on the ground, all this will require ever more accurate and precise waveform models, which would need to include all physical effects. So what I will discuss in this presentation is what does it take to build faithful waveform models for the entire coalescence, combining the different analytical techniques and also numerical relativity, and how perturbative results from scattering amplitude calculation may be employed to improve these waveforms in the future. So let's start with the summary of all the detection done by LIGO and Virgo, and more recently also Kagra's joined the collaboration. Since the discovery in 2015, a total of 90 gravitational are you listening? Are you hearing me actually? Because
yeah,
I'm getting some.
We lost you a little before Zoom dropped you.
Okay. And then the first neutron star black hole was.
We can't see your slides.
This is a problem.
Into the chat my email to send me the presentation.
Okay. Yeah, it might take a little while.
Okay.
Okay, we can see your slides again. Could you go back one slide?
Well, there was no much before. I was just here. I was just discussing this plot.
Okay. Yes. Maybe start at the beginning of this one.
Again. Okay. So this was just the summary of the binary black holes that have been discovered by LIGO and Virgo. And I was saying that the spread in mass for the black holes in blue is between 5 and 100 solar masses. You see here the two binary. yeah, the problem is that I get push out and then it says unmute and then I get muted. I don't know what's the problem.
It just sounds like it's a bad bandwidth connection. Is it possible for you to mail your slides to a person helping here? His email's in the chat.
But then I will be disconnected anyway, no?
Well, if you're not showing your screen, the bandwidth might work better.
Can I try one thing? Let me try one thing.
Okay.
Just 1 second. In March of next year, 2023, with a 4th run, which promises to go to these distances, 160, 190 megaparsec for binary neutron stars. This is the maximum distance at which we will be able to see binary neutron star with the new sensitivity. And this run will last for a year, and then after a year and a half, more or less, we will go to the design sensitivity run which is called O5, which will take data at different periods of time with improved sensitivity. So basically, this is the noise curve of O5. So we will go from several tens to hundreds of compact binary detection per year, or if it will work at design sensitivity, we'll have 150 events per year. And we will still probe, however, binary systems in our local universe, let's say redshift up to 1. Some highlights on the science of the last observing run. So the 14th of August, 2019, a binary with a puzzling companion was detected by the LIGO and Virgo detectors. What does it mean, puzzling companion? Well, the secondary mass was actually 2.6 times the mass of the sun. So between the mass of a neutron star and a black hole, because we think that the maximum mass of a neutron star is around 2.2 solar masses. Moreover, this binary had a large asymmetry in the masses, almost 10. And the more substructure and complexity the binary has, the richer is the spectrum of the radiation. So you will start having higher harmonics, not just the leading order, the leading quadrupolar emission. This is a visualization of the event. You see the quadrupolar radiation 9 seconds before merger, and then the octupolar radiation shows up at L equal 3, M equal 3. And then because the harmonics become more important when the velocity is larger and larger, 4 seconds before merger, you have the L equal 4, M equal 4. And then you have to go very close to merger, 1 second, to start seeing also the L equal 5, M equal 5, that you barely see now in blue here. Now, more quantitatively, using the waveform models that the collaboration has at its disposal from the effective one-body family and phenomenological family, one can actually measure the secondary mass. And if you add higher harmonics, HM, precession in the waveform model, you can get, as you can see from these two posterior distributions, the best measurement of the mass, and conclude, in fact, that this was an unusual compact object. The second example I wanted to make was discovered the 21st of May, 2019, is the largest binary black hole detected by LIGO and Virgo. The total mass was 150. You see here a numerical relativity simulation. And in fact, in particular, the mass of the primary is actually too large to be formed from a collapse of a star because of pair instability supernova that would prevent a black hole to exist with a mass between 60 and 120 solar masses. Now, this event, as you have seen from the simulation on the left, is very short, and in fact poses some challenges from a modeling point of view because, as you can see here, the reconstruction, the two-dimensional posterior distribution of the masses using waveform models from the effective one-body, phenomenological one, and even from numerical relativity simulations that actually this is a model that interpolates directly numerical relativity simulations. You can see some differences in the posterior distribution, still at a 90% overlap with each other, but there are more differences here than any other event that we have discovered. And about the spins in the binary, we measure the projection of the spin perpendicular to the orbital, along the direction of the orbital angular momentum, so perpendicular to the orbital plane. And also we can measure the spins on the orbital plane. A measurement of Chi-P would say that there is some precession. And here you see the posterior distribution for the different families and the prior. And this would say that perhaps there is some signal of precession because the posterior distribution do not actually agree with the prior. Still, the systematics, due to waveform modeling, are not negligible when spin precession and Dyer modes are relevant, as you can see here, but they are still subdominant with respect to the statistical uncertainty. And this will not be the case with future detectors. I remind you the statistical uncertainty or statistical error is set by the signal-to-noise ratio in the detectors. Finally, the last example I wanted to make is the first robust detection of a mixed binary. The 15th of January 2020 was discovered. You see here a visualization of the event of the neutron star and black hole going around each other. And because of the mass ratio in the system, the spin of the black hole, the neutron star is not disrupted because before plunging into the black hole. And so the black hole swallow the neutron star whole. And for this event, also using waveform models, one could reconstruct the masses. And you can see this is the mass of the secondary and the primary. The event is the one in blue, the one that I show you on the left. And the mass of the secondary is between, let's say, 1 and 2.5 solar masses, so it's certainly a neutron star, while the primary mass is between 5 and 10, and so it's certainly a black hole. So ever more sensitive detectors in the next decade, and in fact, in the next decade, we expect new detectors on the ground. In Europe, Einstein telescope, underground, 10 kilometers apart, the arm cavities. Cosmic Explorer in the US, on the ground, 40 kilometers instead of 4 kilometers, like it is LIGO and the two LIGO detectors. On this plot here, you see the strain noise as a function of frequency. With a new detector, there will be an improvement of 1 or 2 order of magnitude, depending on the frequency range. And this is very important. In particular, the extension at lower frequency of this detector around a few hertz will allow to detect binary black holes with large masses. So large mass that they would coalesce around a few hertz, and so they are not visible with the current detectors. So the plot on the right shows the distance or the redshift that this detector will allow to probe. And you can see here that one could probe, in fact, 100,000 solar mass system, binary black hole systems, up to redshift 10 or even larger. So when the universe was populated by the first stars. Now, what is quite overwhelming is to think about the number of sources and the signal-to-noise ratio that this detector will allow to observe. So we will observe each year of the order of 30 binary black hole signals, which last for up to 10 minutes, with signal-to-noise ratio larger than 1,000, and 20,000 binary black holes with signal-to-noise ratio larger than 100. I remind you that the signal-to-noise ratio currently with LIGO and Virgo is of the order of 10, in some cases 20. We will observe each year 10 binary neutron stars, which will last several hours in band with signal-to-noise ratio larger than 500. This will be very important to nail down the equation of state of neutron stars, and we will have several hundreds of binary neutron stars that will be able to observe with signal-to-noise ratio larger than 100. Now, another important fact is that the signal will be also more complex, going to larger masses. One will go also to larger mass ratios. So we will be seeing the system like intermediate mass ratio in spirals, having mass ratio of the order of 1,000. And you see here two snapshots of the dynamics of these events at 1 Hertz and then after 10 Hertz. And then in space, we will have in the next decade a detector called the LISA. This is mainly a European Space Agency, but with a large contribution from NASA. By next year, LISA hopefully will be adopted, as we say, by ESA. And at that point, the flight is supposed to happen in 2035. And LISA will open a new frequency band around the millihertz for 3 decades, and will allow to see binary black holes of millions or billions of solar masses. We will see them sweeping in band for a year or for months. With very large signal-to-noise ratio. We will see extreme mass ratio in spirals. You see here one event with different multiples. These are the tracks of the events. We will see white dwarf binaries in our galaxy here in gray. And also these tracks represent stellar mass black holes of the kind we are detected with LIGO and Virgo that will be first seen in LISA, and then after months or a year be seen on the with the detectors on the ground. At the time will be Einstein Telescope and Cosmic Explorer. With the large signal-to-noise ratio, we will be able, if they exist, to observe new fundamental particles forming boson clouds around black holes because of superradiant instability and emit gravitational waves. And with a large signal-to-noise ratio, we will be able to probe the physics close to the horizon, perhaps detecting possible signature of a surface which is not completely absorbing as it should be an horizon, but with some reflectivity. Okay, now to take full advantage of the discovery potential, we need to have more accurate waveform models. And I want to start with an example. And this is one of many that you can have from the literature that shows that systematics will dominate the statistical errors with future detectors and also with the next runs, actually, if we don't improve the waveform. And I take the example from this paper where they showed that they basically consider many events, many binary neutron star events. If you stack them, if you combine them, you can reduce the statistical errors. But what about the systematic biases? Is it one going to be dominated by that? And so let me show you this plot. So this plot, it's an attempt to measuring the radius of the neutron star with a neutron star with a mass of 1.4 solar masses. The radius is in kilometers. So and this is an example, not even for future detectors, but for the run design sensitivity of LIGO and Virgo, 05, the one that I mentioned you at the beginning of my presentation. Now, what they did is that they considered a synthetic signal. They injected a signal with a certain waveform model, many signals, 38 of them, and then they stack together, and they obtain in blue the posterior distribution that says that you can measure the radius at the level of 2%. But then they also recover the signal with other waveform models. For example, another phenomenological model with different tidal effects, a pure post-Newtonian model, an effective one-body model. And what they find is that, for example, if you use a model which has a different binary black hole baseline, so no tidal effects, only the vacuum part, sorry, not the vacuum part, the binary black hole part, you can see that there is a displacement of the posteriors, which indicates the presence of a bias. And also when you use a model which has the same binary black hole baseline, but you change the tidal corrections, you also can have, a difference. So basically the bottom line is that although in principle you can measure the radius of the neutron star with 38 events, after 38 events with 2% of accuracy, which by the way corresponds to 250 meters, the systematic differences between current waveform models can be twice as large. So this is not good. And this is just for the run of 05. I was telling you that with the next generation detectors, we will have a signal to noise ratio of the order of 500. So this is a huge problem. So this means that it's crucial to make a binary black hole model more accurate, but also tidal corrections needs to be improved. And you can look at other examples in the literature to see other cases in which these systematics show up if we don't improve the waveform models. So in order then to improve the waveform models, so we have to, again, solve accurately the two-body problem in general relativity. In the last 15 years, this has been done by combining analytical and numerical methods. And among the analytical methods, we have post-Newtonian theory, which expand the Einstein equation in powers of V over C, or GM over R C square. And then we have post-Minkowskian approximation that especially thanks to this community, actually the scattering amplitude community has provided a lot of new information in the last few years. It expands in G, which is the Newton constant, and it doesn't expand in these velocities, which means that this is suitable in particular for fast motion, but still a weak field. And then we have the gravitational self-force that expand in the mass ratio, the Einstein equations. And although this was originally developed for extreme mass ratio in spirals, so when the mass ratio is 10 to the 5, 10 to the 6, as you will see later, it seems to be quite actually effective even for mass ratio much smaller than that, of the order of 10. So for what concerns then this presentation, because this is also the work that I've been doing in the last 15 years, these approaches can be combined together in the effective one-body formalism and made more accurate via numerical relativity. So in view of what I was saying before, with the next generation detectors, the future runs, the next runs with LIGO and Virgo, we need all these approaches. And by the way, I didn't also mention perturbation theory, because when two black holes merge, they form a new black hole, the black hole rings. And so we need also to represent the quasi-normal modes of the black holes. And of course, numerical relativity, I don't think actually I mentioned it from the plot. Numerical relativity is very important, but is confined to a certain region of the parameter space. So based again on work in the literature, for example, this one, we would need to improve the waveform accuracy by 2 or more order of magnitude, depending on the parameter space. And I'll show here this beautiful table that has been just updated for this presentation by Justin Vines, which represent the results today in post-Newtonian approximation, and also here post-Minkowskian. The one, and here actually is the spin, okay? And I want to highlight a couple of things. So in the last few years, we have made progress, although not complete at 5pn, and also 5.5pn spin orbit, but also spin effects have been completed 4.5pn, 5pn, 5pn actually, the spin square terms. And also we have access, as I will say also later, to the S to the 5 terms. So this is very good news, but order of magnitude means that very likely we have to go to 6pn, which in post-Minkowskian expansion would mean 7pm or 6 loops. We need to maybe combine these methods in a more effective way if we want not to go to these very high post-Newtonian orders. Maybe this might be possible. Another important thing is that as we improve the waveform models, we also have to improve the numerical relativity waveforms, because also they will not be, the current one will not be accurate enough for the next generation of detectors. And also we need to extend them in region of the parameter space where the parameters are more extreme, in particular in the mass ratio, in the spin, and the eccentricity. And finally, perhaps all this work, working together may lead to new strategies to solve the two-body problem in GR or beyond, and perhaps unify the description of bound and unbound orbits. Now, I wanted to make a couple of highlights before going into a little bit more detail how we build the full waveforms. And I want to start with the highlight from the post-Minkowskian side. This has been quite important. At 3 p.m., the conservative dynamics, which means the Hamiltonian, has been computed. It is local and valid for generic orbits. At 4 p.m., there have been results, especially last year, but they are the non-local part in these results is for the moment restricted for hyperbolic orbits. And so one thing you can do is to compare these results with numerical relativity results to see how they compare. And this is an example of the scattering angle in degrees as a function of the impact parameter. You see here the numerical relativity result in black, and the post-Minkowskian results are different post-Minkowskian order up to g to the 4. And you can see that there is an improvement toward the numerical relativity result. This was for an equal mass, of course, non-spinning, because these results are non-spinning. I wanted also to highlight the fact that although this is computed for the conservative part of the dynamics, the post-Minkowskian scattering angle, you can actually add the radiative effects that you can extract using results from a paper of Byrne and Moore from the numerical relativity results. And you can see that the impact of the radiation reaction effects or dissipative effects is not very large on the scattering angle. I wanted also to highlight that this computation of the scattering angle is not really in the regime where post-Minkowskian should be applied, because this is the large scattering angles, and the post-Minkowskian is more suitable because it's an expansion in G in the weak scattering angle case. And the other plot I wanted to highlight is now you can compare with the binding energy. Although this result, the non-local part is only valid for hyperbolic orbits, we show in this paper that we can assess the impact of going to the bound case, looking at post-Newtonian calculations and seeing what's the difference between hyperbolic and elliptic orbits. And having assessed that that is a small effects, we use actually the Hamiltonian, this one, to build this plot at 4 p.m. So you see here the result against the binding energy, again from numerical relativity, which is in black. And you see the 1 p.m., the 2 p.m., the 3 p.m., and the 4 p.m. Of course, this is just an estimate, the one of 4 p.m. There are no dissipative effects here. And also, again, let me stress, this is computed from this Hamiltonian that use the non-local part, and we look forward for the extension or the completion of these results for bound orbits. Now, the other example I wanted to make about the new results in the modeling concern with the gravitational self-force. After many years of work, the self-force people were able to compute the second order in mass ratio effects for a non-spinning binary in quasi-circular orbits. And although the gravitational self-force approximation is designed for cases in which the mass ratio is extreme, as I was saying, mass ratio 10 to the 5, 10 to the 6, it also performs remarkably well for comparable mass ratio, let's say, of the order of 110. Actually, also for mass ratio 1 is not so bad, but I'm going to show you the result for mass ratio 110. So this is the waveform as a function of time for mass ratio 110. In black, you have the numerical relativity result, and in blue, the result of the waveform in gravitational self-force when you use the first order results, and in orange, the second order results. And you can see that with second order, you can go almost up to basically the plunge. This is very close to the plunge of the two objects, and you see that there is not a large dephasing, which is present if you were using the first order self-force. Okay, so now how to take advantage of new results in building, waveform models. Okay, so now let me discuss the effective one-body framework and how this has been done, and then can it be even improved more with post-Minkowskian calculation, hopefully. So in the effective one-body formalism, we map the two-body dynamics of two bodies going around each other with some spin in a dynamics of an effective body, which has the mass, the reduced mass of the system, moving around a deformed black hole, which has as a mass the total mass of the binary. And in this particular representation of the effective one body, we put the spin, the total spin, to the central body. And this effective one-body formalism provides a new Hamiltonian in the real description, which is linked to the Hamiltonian in the effective description through this relation here. Now, for simplicity, I'm going to restrict to the case in which the spin are aligned with the orbital angular momentum, so only equatorial orbits, but the model is available for generic orbits. And now this effective Hamiltonian, at least in this representation that we developed in this paper with Mohamed Alil and Jan Steinhoff and Justin Vines, up to 4pn order, the even part, even in powers of the black hole spin, can be represented by this, symbolically by this equation here, symbolically because I'm not going to give you all the potential that enter here in the Hamiltonian. And the odd part, besides depending on the canonical variables, depends on the gyrogravito-magnetic functions that I wrote here. And now what I want to stress, and you will see this in the few slides, is that when we built an effective one-body model and we need to calibrate it to numerical relativity, and I will indicate with a color cyan function or coefficients that are going to be calibrated to numerical relativity. So there will be a coefficient here at 5pn, because I remind you that 5pn is not known today, and also a coefficient at 5.5 post-Newtonian order, which is a spin orbit term, which is not known today, that are going to be calibrated to numerical relativity. Okay, so you have an Hamiltonian. What do you do with the Hamiltonian? You can, compute the Hamilton equations, and which I wrote down here. The spin can be evolved by taking Poisson brackets with the Hamiltonian, but you need a radiation reaction force. So the Hamiltonian I was showing you in the previous slide is resummed. We say resummed, okay? And the force also needs to be resummed. And here I don't have the time to explain to you, but I want to say a couple of things. So first, the force has been mainly developed for quasi-circular orbits, although at the end you will see some examples for the case of eccentricity. But the force is written in terms of the modes during the inspirals. And also these modes need to be resummed. So we don't basically use modes just post-Newtonian expanded in V over C, but they are factorized in different pieces. And there is a source term, a resummation of the tail terms. There are also corrections that go beyond the quasi-circular motion that are tuned to numerical relativity. So I'm trying to stress that we need a resummation of the Hamiltonian, a resummation of the potential in the Hamiltonian, a resummation of the radiation reaction force to get very good agreement with numerical relativity. And I want to make an example, because this is quite simple, in the non-spinning case. In the non-spinning case, the Hamiltonian becomes quite simple. There is only one term that I wrote here. I wrote in explicit form the potential that enters in the Hamiltonian, in the non-spinning Hamiltonian. So 1 minus 2 over r will be the Schwarzschild value. And then we have correction at 2pm, at 3pm, at 4pm. And this is the unknown term. And even this potential, in order to have very good agreement with numerical relativity in the non-spinning case, we need to resum this potential. And I give you here the figure that actually show the resummation of the potential divided by r squared as a function of r. Because when we go in the strong field, using the Taylor expanded form of the potential does not allow us to obtain very good agreement with numerical relativity. Now, from your course in general relativity, you might remember that actually the peak of this object here determines the photon orbit around the Schwarzschild black hole, which is basically also called the light ring, which is at 3m. And basically, we need to extend this photon orbit idea also to different mass ratios. And we need to do it in a smooth way. And this is what actually the resummation of the potential allows to do. And you will see in a moment why this is important. Okay, so now let me say how we then conclude this and build a full waveform. So we evolve the Hamilton equation with the radiation reaction force, and we compute the waveform on the dynamics in the spiral part, the plunge part, up to the photon orbit. This is the evolution of the gravitational wave frequency. When the two black holes merge, they form a new black hole that rings, emitting quasi-normal modes. And this is the frequency of the least quasi-normal mode. So how do we complete the waveform? Well, in the 70s, people were realizing that the quasi-normal modes are excited at light ring crossing. And in fact, we use this idea. So when the effective body in the effective description pass the effective photon orbit, it triggers the emission of quasi-normal mode. And so we complete the waveform from the spiral to merge ring down by basically adding quasi-normal modes. And we use a particular function that has a part that depends on time, and then the quasi-normal mode, the damp sinusoid, are here. And again, these functions are also improved using numerical relativity. They are also in Zion, as I was telling you before. So the full waveform is built basically from the spiral plunge and then the merging down, imposing the continuity of the waveform at the matching point, which is close to the photon orbit in the effective description. Okay, so then what do? We have basically a semi-analytical model that we can improve by tuning all these terms that I was showing you in Zion. And so we do a calibration to numerical relativity in steps. We start from a numerical relativity waveform compared to the effective one-body waveform without any calibration. And you see that after a certain number of gravitational wave cycles, we have a dephasing. And then we start tuning this coefficient, this function in Zion until they agree very well with each other. And in the last model that was used by the LIGO and Vigo collaboration, which was the fourth generation model as UBNR before, we repeated all this process for 141 numerical relativity simulations that were at our disposal from the Simulating Extreme Spacetime collaborations. So which are all the dots here, the green and the blue. We use also Tiokovsky equation waveform in the small mass ratio limit. This is, by the way, the combination of the spin in the binary. And then we extrapolate the model everywhere else, and we use some numerical relativity waveform to validate the model. And then once the model is available, it can be used for LIGO-Virgo template banks, for inference studies, for tests of general relativity. Okay, so this is good, but now considering the recent developments and improvements on the analytical model, we went further. We tried to improve and develop a new model, the fifth model, V5, for the new upcoming run, O4. I want to introduce a quantity that I'm going to refer to in the few next slides, which is called the unfaithfulness. So until now, I show you agreement with numerical relativity using the scattering angle, using the binding energy. But what we care about is really the full waveform. That's why I spent the last 4 or 5 slides to show you actually how, at the end, we assess that we have a very good waveform. We have to use the entire waveform to compare to numerical relativity. And we can compute the overlap between two waveforms, a numerical relativity waveform and the model using this formula. And basically, if we then take the same parameters in the two waveform and just maximize on time and phase and take 1 minus this quantity, this is the unfaithfulness. Basically, the unfaithfulness is 0 if the numerical relativity waveform and the model are matched perfectly with each other. So this is the results of the unfaithfulness with the new model that we have built in the non-spinning sector. So this was the previous model, V4, and this is V5 against a certain number of numerical relativity waveform. So we could improve the median at the level of an order of magnitude, factor 10, basically. And what does it mean that we improve by factor 10? Notice here, this is 10 to the minus 3, this is 10 to the minus 4. This means that we will be dominated by systematic errors at signal to noise higher by a factor square root of 10. Now, this is not enough for the next decade and even for 05, but it was not trivial to achieve just a factor 10. And for the non-spinning sector, I want also to show you the agreement with the binding energy from numerical relativity. When we go from the fourth V4 model to the V5 model, we go from the dashed to the continuous line, and now we are completely within the numerical relativity error for the binding energy. So this is a very good result. And now looking at the spinning sector, so extending these results also to spins. So this shows the unfaithfulness, the maximum actually unfaithfulness against 450 numerical relativity waveform. Part of them were used for the calibration. And you can see now here that also in the spin sector, we can basically improve by an order of magnitude the unfaithfulness. And this was the distribution of the numerical relativity simulations that were used for this calibration. And this actually is the scaling color of the unfaithfulness, which is almost all below 10 to the minus 3. Now, another interesting result is that when you compare the results of V4, V5 with the numerical relativity error, we are not completely, with the new model within the numerical relativity error for numerical relativity, the error for numerical relativity. But this plot tells you that if in the future we are going to have another order of magnitude of improvement, we will need to improve also the numerical relativity waveform. So this is also quite important. Okay, so now I want to go back to post-Minkowskian. So I was trying basically to explain to you that, so I have 5 minutes, I understand, I saw the chat, yeah. I think I will be able to do that. Now, when we go back to the post-Minkowskian results, this is the plot I was showing you before of the comparison with the binding energy of numerical relativity and the post-Minkowskian results. And these were the results just taking the post-Minkowskian Hamiltonian, just the vanilla one, and computing the binding energy. But now if we include this post-Minkowskian result in the effective one-body description, using the same range here, you see the result, and there is much better agreement with numerical relativity curve, even if we don't consider the 4 p.m. results, even the G2, and actually this is the G3, the third post-Minkowskian order. And how these results are obtained in the effective one-body description? These are non-spinning. So I go back again to the effective Hamiltonian, and we don't use the same gauge and the same parameterization of the potential that I showed you before. So what we do is that we introduce the post-Minkowskian parameters, post-Minkowskian results in a function here that enters the effective Hamiltonian. And we determine these post-Minkowskian parameters by matching the scattering angle that you compute from this Hamiltonian from the one that you compute in the computation that was done in this paper for the 4 p.m. results. And of course, this is only the first step, because as you have seen before, if you want really to understand now whether these results could be useful for building the waveform model, unfortunately, you have to go through all the other steps that I was showing you. You have to add the radiation reaction force. You have to compare with numerical relativity. You have to build the full waveform. And only at that point, you will understand whether there is really an advantage of using an effective one-body approach based on post-Minkowskian results. So I wanted to show you also I wanted to comment now about another point. So this is again the same plot I showed you here, is just in a different scale on the y-axis and on the x-axis. So these are again the 1 p.m. result, 2 p.m., 3 p.m., and the 4 p.m. And I'm contrasting now the 4 p.m. with the results that you would obtain if you post-Newtonian expand the 4 p.m. results in the effective one-body description and truncate a 3 p.m. order. Because as you know, the 4 p.m. results contain the 3 p.m. Approximation. Now, for the binding energy, the 3 p.m. Are actually closer, as you can see, especially in this part here. But for the scattering angle, actually, that is represented here. This is the fractional variation of the scattering angle. These results are actually at 4 p.m. closer to the numerical relativity results with respect to 3 p.m. But again, let me emphasize that to assess the accuracy of the p.m. Hamiltonians, dissipative effects need to be included, the resummation of the EOB potential, the calibration against numerical relativity will need to be pursued. Okay, so I wanted to say a few words about the importance of post-Minkowskian calculation for the eccentric problem. And let me just say that the eccentricity so it's very important to include also for systematics, and has been done in some of the effective one-body models for the binary black hole coalescence, dynamical capture. But where post-Minkowskian can be interesting is that, so what I want to say here is that I think post-Minkowskian for the eccentricity problem has an advantage with respect to post-Newtonian, because if it is true that it's more accurate for scattering encounters at large velocity, this also means that post-Minkowskian is more accurate large eccentricity at fixed periastron distance. And so I actually look forward to employ post-Minkowskian results for the extension of the effective one body to eccentricity. So let me conclude. I think I have 1 minute. So the scattering amplitude methods have brought a new and fresh perspective and tools to solve the two-body problem. Besides progress in the non-spinning case, which have been focused on, perturbative results in PM have also been extended to the spin sector. And these are some of the papers. I'm sure that I missed some of them, but there have been a lot of work, in particular for the extension of post-Minkowskian result in the spin orbit sector. So far, the EOB Hamiltonians have been mostly based on PN results with some contribution from GSF. But given the recent important developments in PM and GSF, it will be very important, and I'm very eager to explore Hamiltonians of the EOB approach based on PM and GSF. They could also be completed with PM calculations. Until the full calibration of EOB waveform is performed, it is difficult to assess the actual gain of a new higher order result in PN. In order to improve by a factor 10 the unfaithfulness, we had to do so much work to resum the potential and use particular gauge to write actually the Hamiltonian. Perhaps this may change if we use EOB Hamiltonian based on PM or GSF, I don't know. Scattering amplitude may be more effective, perhaps, in pushing perturbative calculation at higher order, may even suggest new way of resumming the building blocks. And finally, in the future, we might not need Hamiltonians and radiation reaction forces, let's say gauge-dependent quantities, to construct high-precision gravitational waves. But currently, I must say, this is the only way we know how to do it. And so thank you very much for your attention, and sorry for all the problems with the connection at the beginning.
Thanks, Alessandra, for a very exciting talk. We have time for a few questions. Well, the audience is, okay, Josh, there's a question. Josh Shen, please.
Hi, Alessandra, this is Josh Shen. So thanks for a beautiful talk. So you mentioned that in the scattering angle, the dissipative effect is a little bit surprisingly small compared to the conservative part in the scattering angle. But I was wondering what happened to the actual binding energy? Can you see how important is the dissipative effect? For example, in PN, you can consider leading, next leading part, and how much does that change to the agreement with numerical relativity?
So if I understand your question, you are saying, the effect here on the scattering angle due to the dissipative effects is very small, and you are asking what will happen if I add dissipative effects here?
Yes.
Yeah, so actually this, there is a plot in the paper with Andrea Antonelli that we wrote in 2019, where in the case of the post-Minkowskian results at actually 3 p.m., we added the effect of dissipation. And it goes in the right direction, it brings the curve actually down, it's not a huge effect, but is not negligible. And when you, again, I want to make this point, to reach values of unfaithfulness of 10 to the minus 3 that I was alluding before, details like variation of a few percent of this curve is very important. So if you want, the dissipation is important to add, but the shape of how the post-Minkowskian results are incorporated in the the effective one-body approach will also play an important role. So you have to take into account all these aspects, okay, if you want to get really at the end the right answer. I hope I address your question.
Yes, so thank you.
There's a question in the back over here, maybe Demetrius, I think.
Hello?
Yeah.
Hi, thank you for the very nice talk. It's, I guess, a similar question like Jason. The agreement between the 4 p.m. and numerical relativity looks really good, despite of the fact that 4 p.m. is for hyperbolic orbits. So could you comment on the importance of actually understanding the bound problem instead? It seems that hyperbolic is enough.
No, okay. I hope I didn't give this impression. I think it's very important to actually complete the 4 p.m. for bound orbits, which means to extend the non-local part to bound orbits. It's true that here, in particular, when you put it in the effective one-body description, you have a very good agreement with numerical relativity. And however, this is obtained with a particular resummation of the potentials, okay, first of all. Second of all, in this paper, we actually estimated the impact, the difference between the elliptical and hyperbolic effects in the context of Pn at this order, and we found that the effect was small. But it doesn't matter that it's small, it needs to be included, because we need to, there is no reason why this calculation should not be completed, first of all. And we need a complete result, and then with a complete result, we can add other effects. So, but I didn't want to give the impression that we should just stop here. If you are asking why the hyperbolic is working so well, it seems that these corrections, the correction, the difference with the bound case, at least for this non-local part at 4 p.m. is small. But I don't have a first principle answer to your question, if that is the question.
I see.
We just found that it's small.
Thank you.
Maybe I can ask one quick question.
Yeah.
There's two usages of these waveforms. One is for discovery, digging it out of the noise, and the other is for precise measurement of parameters or tests. I want to know which is more important going forward for future improvements in precision. Which does it affect more? Or maybe
okay.
it depends.
Yeah. Let me put this slide. So when you detect a signal, you don't care about the parameters, in the sense you might detect a signal with the wrong parameters. And in fact, we do see that, in the sense the parameter that come from the template bank, the masses and the spins. The template bank has only the spin perpendicular to the orbital plane. There are is four-dimensional, the template bank, the two masses, the two components of the spin perpendicular to the orbital plane. And this parameter can be quite different from the one that come out from the Bayesian analysis when then we do the inference, okay? Now, of course, it's more important the waveform model that is used for inference. But the one for the search will become more and more important in the future. For example, the search at the moment does include eccentric effects, or does include precession of the spins. And so if in the future that we want to maybe see, signals that are more subthreshold, that are smaller SNR, but they are very important, they are more unusual maybe, spin precession, eccentricity. We also need to use this sophisticated, more precise templates also for the search, okay? But of course, you know, all the waveform that I use for inference are very important, like the one for this test. Yeah? This is an inference test, and you need to have very good waveform if you want to get the radius of the neutron star at the level of 2% and not be dominated by the bias due to the systematics.
Great, thanks a lot for that answer. I think we should now move on. Let's thank Alessandra again for a great talk.
And I think at the end, my phone was much better than the connection through internet, the place where I am.
Okay, bye. So our next speaker is Zvi Byrne, and he's going to tell us about applications of scattering amplitudes to gravitational waves.
Hello? Yeah. Okay, well, first I want to thank the organizers for asking me to speak, and also this absolutely wonderful conference. So I'm going to give you an update on work we've done in the past year. So it's work with Julio Para-Martinez, Radu Roiban, Mikel Roef, Jiaoshen Shen, Mikel Solon, Mao Zhang. And then for the spin part is Dimitris Kosmopoulos, Andres Luna, there's Fei Tang as well. And in work that we're doing right now, there's Trevor Shepner. So of course, as we just heard in great detail in the really excellent talk from Alessandra Bonanno, the era of gravitational wave astronomy has begun. And what I will talk about here is the completion of the G to the fourth conservative part of the spinless two-body interaction. And also, I'll talk about spin effects, and then say a little bit about the outlook. And there's going to be many more talks, of course. So just to set the stage, we're talking about the two-body interaction. And I'll be talking about the conservative part, and we heard in Alessandra's talk about the importance of that. And the basic idea is we're trying to correct Newton systematically. So there's a post-Newtonian Hamiltonian. So it's the first term is Newton. The second term was worked out Einstein, Infeld, Hoffman, and also earlier work. And then over the years, people have been systematically working through higher and higher orders of perturbation theory. There's the fourth post-Newtonian, which you can see is relatively recent. We are working in the post-Minkowski framework, and Alessandra in 2018, she came to Amplitudes and gave us marching orders. I suppose she just did that again. And in her talk, she explained what needed to be done. So in this chart here, so this is exactly her transparency from then. She explained about the post-Newtonian corrections. So you're expanding in velocity. You're expanding in velocity, you're expanding in Newton's constant, the 1 over r just means Newton's constant along these columns, and then she said, she explained about the post-Minkowskian, what needed to be done. She said, third post-Minkowskian order, that's the one that needed to be done, and that included some pieces that were not known in the fifth post-Newtonian. So that was pretty simple, and we also had a very nice paper from Thibaut Damour that explained also the same thing of what needed to be done. Now, I'm not going to have the time to explain all the techniques we use, but the basic idea is we import all the knowledge that we have from amplitudes, from quantum field theory, in order to help with this problem of the determining the two-body interactions in general relativity. And of course, we have gotten very, very good at perturbation theory, in gauge theory, gravity theories in the context of scattering amplitudes. We have all our methods. There's the unitarity method. Of course, we have double copy relating the gravity to the gauge theory. There's more technical methods having to do with how to extract the classical part of the integrals, the method of regions. There's EFT methods. of course, we heard a lot about integration by parts. This is crucial for what we're going to do in method of differential equations. And the basic idea is we leverage all the knowledge we've gained over the years in order to help with this problem of gravitational radiation. And there's actually many methods already. So the method that we use, this was Chung, Rothstein, Solon, where they laid out exactly how to extract the Hamiltonian. As you heard from Alessandra, the importance of the Hamiltonian in the way things are being done today at the observatories. And this uses EFT matching to extract the potential, which we then construct the Hamiltonian from. There's this very nice formalism, K-Mach. That's, you calculate directly physical observables. That's very popular now. Iconal phase, that's an oldie but a goodie. There's amplitude action relation. I'll say just a little bit about that. It's a somewhat slicker way of extracting basically we get the radial action out of it. There's exponential representations, heavy mass field theory. There's a lot been written about spin. I'll be talking about spin here. There's worldline formalisms. Worldline is not exactly amplitudes, but now there's a lot of overlap between the approaches. Okay, a long story short. So it was the third post-Minkowskian conservative part that convinced our friends in general relativity that we amplitudes people are actually useful, that we can do something of interest to them. This is the amplitude in the classical limit. It's remarkably compact given that it's fairly high order in general relativity. From here, there's some observations which actually fed into the field, into other approaches. And that's that the mass dependence here is very simple. And this led to a comprehensive understanding by Damour, who uses it quite effectively. And from here, you can get the Hamiltonian by the EFT matching. You can extract potential and a Hamiltonian. Now, one of the key questions in all this game is, how do we know it's right? And that's not a simple question. If you have a new technique, new ideas, basically you come from left field, you want to know, did you do it correctly? So, of course, what we did, the original check was comparing to post-Newtonian results, and that's done by expanding in velocity. And then, of course, the format is completely different, so you have to find yourself a canonical transformation. And that verified that we thought our expression was correct, so we published. Thibault, on the other hand, he didn't like our answer. He was very concerned with a certain logarithmic singularity in it. And in fact, he wrote the paper explaining what the correct result would be. You can look at this paper, version 1, if you're curious what all that was about. But anyway, within about a year, there were multiple calculations. So 6pn. So Thibault was so eager to prove us wrong that he went off and he did a 6pn calculation. But in fact, he verified our result, so that's good. So that, anyway, I'd say that it was this that convinced the field that we were actually doing it correctly. And there's also subsequent calculations and other ways. So I think it's fair to say that the community now accepts that this is done correctly, the methods work. So that's actually quite important. Now, it turned out that doing that calculation only increased the appetite of our general relativity friends. They said, very nice. OK, how about the next order? OK, so that's what we did. Basic ideas are the same, except it's more complicated. You have to calculate more unitarity cuts. And the integrals are significantly harder. Let me say a little bit about that. So the high loop integration, that's definitely a challenge as you start moving up in loop orders. So in order to do that, we developed a hybrid approach using various ideas from different, from different ways of doing it. So we use method of regions. It's very basic to the way we organize the integrals. There's non-relativistic integration. That's the way we actually did things originally at 2 loops. And what this, the way this is done is you velocity expand. So effectively, you're doing a post-Newtonian, and then you can mechanically integrate. The integrals are relatively straightforward. And what this gives us is boundary conditions for differential equations. So as we all know, the proper way of doing things is by integration by parts. So there's the integration by parts identity, the usual techniques that were discussed in many talks here. What makes this work very well is an observation. It's this paper. So this is from Julio, Miquel, and Mao, that the integrals that we're interested in are single-scale integrals to all loop orders. When we realized that, of course, we were in integration by parts heaven, because the technology that's applied to QCD is for much more complicated integrals. So then that made the problem much, much simpler. And then to figure out what the values of the integrals are, of course, we just use differential equations using the techniques that we heard about in other talks. There are many tools available. Modern era is great. You need to do an integral. You download some software. You just do it. Fire 6 is very good. It's the program that we used. It's more than sufficient at 3 loops. We do encounter elliptic integrals, but despite the worry that maybe there'd be a problem, in fact, it's just a minor annoyance. It's not really a big deal. And here's the answer, what it looks like. So this is the conservative part of the scattering amplitude. This is taken in the classical limits. There's some pieces here which you actually don't need to evaluate. They're iteration pieces. And that has to do with this amplitude-action relation. You can ask, what is a scattering amplitude in the classical limit? Well, we know the answer. It's the exponential of the radial action. The radial action is the quantity that gives the scattering angle if you differentiate with respect to the angular momentum. So this nice organization takes away these iteration pieces, which are a little bit annoying. And then here's what the answer is. There's a piece in here called tail effect. There's a logarithm. There's a non-locality in this. And that non-locality is actually quite annoying. Alessandra mentioned the non-local part. But in any case, this is the answer in terms of the amplitude. And this object, the way we do it is we use Feynman I epsilon prescription. Last I checked, if you want a scattering angle from a scattering amplitude, you work with Feynman I epsilon. That is the correct thing, of course, for the quantum world. And then if you want the classical answer, you just have to be careful about taking h bar goes to 0 appropriately. So there's no real problem about what the prescription is. And then at this level, at least, we match exactly what Damour said about obtaining the conservative part. There's the principal value prescription. These two are identical. If you take the real part of the Feynman answer, it exactly matches what Damour said. So we're quite confident that we have defined the conservative part in a good way. And this, in fact, is the complete conservative contribution. Now, this question of how do we know it's right, there's a lot of subtle issues you have to worry about. It turned out that Bini, Damour, and Geralico, I suppose they were so eager in getting our answer that they even, in their paper, they converted to our notation, right? General relativity, writing down scattering amplitudes. And the purpose is, they gave the 3 terms here, and then they said, this is what we're supposed to find in our calculation. And indeed, that's exactly what happened. They made our life quite simple in that way, that we didn't have to convert notation. They converted their notation to our notation. That was really great of them. We really appreciate that. And of course, you can see from these numbers, this is highly, highly non-trivial to match that. So clearly, we're on a good track here. But it seems that every time we do one of these calculations, there's some controversy. there's some disagreement with one of the terms that's in Blumlein and his group. It's called second cell force. He had what's called a second cell force. It's just one piece. The rest of it agreed. And then shortly after our paper, there was another paper from Porto and his group and their calculation, and they claimed that we drop something they call memory pieces. And let me just say, we disagree with that. So what's the status? Well, I think that these disagreements, they still need to be ironed out. There's still some issues to be thought through, but thanks to Damour, I think everyone is lining up. He calls it good polynomiality. Maybe a clumsy English there, but at least the physics is very clear. He just says, you cannot have this in the scattering amplitude or in the impulse, 1 over m1 plus m2. The reason why we can't have it is because in the scattering amplitude, it's not there from our point of view. Needless to say, this put the fear of God into anyone who had a term like that. And there's also a forthcoming paper I should mention from Byrne, Bohr, Van Hove, and Planté. They also match our result. Now, there's an issue that Alessandra alluded to. At this order of perturbation theory, it's not as simple as you might have thought to go from the unbound case, hyperbolic orbits, the scattering orbits, to the bound ones. And this has to do with what's called tail effect, a non-locality. It depends on the history. And this issue, it's well studied in the PN expansion. What is not known is if you start from the unbound, how you can just immediately jump over to the bound case just by doing some kind of an analytic continuation. I hope that this thing will be solved pretty soon. Now, there's also great progress on the dissipative part. There'll be a talk from Shen, a very beautiful paper, Manohar, Ridgway, and Shen. Anyway, he'll explain it very well. It's very interesting. Now, for the rest of the talk, I want to talk about spin. So there's two issues I want to focus on. One question is how to define an EFT for the Kerr black hole two-body interactions. This is not known, not from general relativity. In principle, it can be known by computing hard enough. But of course, we do it the Amplitudes way, is spot a pattern, write down the answer, okay? Or a guess for the answer. And there's something we encountered, which is a little bit mystifying, which is a very basic question. How many physical parameters are needed to describe a generic spinning object like a neutron star? Or in the language of EFT, how many Wilson coefficients do you need, independent ones? Our results suggest there's more than had been previously appreciated. So how do we do spin? Let me show you the basic setup. We start with an EFT of particles with arbitrary spin. There's a Lagrangian we write down for the interactions. To get this Lagrangian, all we needed to do is look at Levy and Steinhoff and a one-to-one correspondence between the world line description and what we wrote down. You just write this down immediately by looking at what they have. It's in terms of M is a Lorentz generator. Remember, this is quantum. We're still thinking about quantum field theory. So there's no spin. There's just Lorentz generators. No classical spin, that is. And then at the end, you have to go to the classical limit. So you have a bunch of Lorentz generators. It's sandwiched between the polarizations of these massive particles. And there's a connection that you can write down between the Lorentz generators and the spin tensors. You can convert between the spin tensor and the spin vector. It's standard. This is completely standard. And I should say that in the way we constructed this, in terms of rest frame spin, this condition, P mu, S mu, is equal to 0, it's a triviality. It's just immediately obvious if you're working in the rest frame. Now, in the context of quantum field theory, you can write down infinite classes of other operators. So that's what we have. Here's, well, we'll call this the H class. There's more classes of these objects. So H class is another set of operators, just the way the indices are contracted. Here would be an example. This would be the H2, the second term in this series. So there's more and more Lorentz generators, more and more spin. This one here is very analogous to a magnetic moment term in electromagnetism. Here's another one not in this series. We'll call this the D series. This is where you have a momentum dotted into the corresponding Lorentz generator. Over the years, people have been studying these Lagrangians. Like here's a little fact. If you take H2 equals 1, that improves the high energy behavior of the Compton amplitude. And that was papers from Parati and others. Okay, and the black hole solution also picks H2 equals 1. That's another little fact. And then if we look at a 3-point matrix element in the classical limit, this Lagrangian is redundant. Basically, you take P mu, S mu nu, you take that at the end of the classical limit, you're on shell, and the extra operator is redundant. This one, in particular, you're going to get a P dot S. It's just going to be 0. This operator will disappear. These types of things, they're called spin supplementary conditions. Okay? And that's used on the world line to define exactly what you mean by spin. And there's other operators. There's a whole zoology of this. There's no complete classification of this, but anyway, there's R-square operators, which they're important for defining what you mean by a black hole, for example. And I guess they're important because if you want to describe a spinning object, you need every operator, every independent operator. Okay, some consistency checks. At 3 points, we know exactly what we should match. Justin Vines wrote down the energy momentum tensor and in fact said, if you want the black hole, that energy momentum tensor, these coefficients with this normalization, they're all 1. And at this level, if we go, just take the energy momentum tensor and go on shell, then the coefficients are redundant. You see, like the different series that we had, it appears together as a sum, so it doesn't matter which one you pick. So there's a redundancy at the level of 3-point on shell. And Compton, well, some good news from a few days ago. So Justin Vines and friends, they carefully calculated Compton using world line techniques, and they say that our Compton, it matches through S cubed with the one recently obtained from the world line. And the Compton is very important because it feeds into the next order of perturbation theory. If you want, instead of order G, you want G square, then here's the Compton amplitudes, 2 Comptons sewn together. Okay, so let's do our guessing. Well, a lot is known about the black holes through G square and S to the 4th. So this would be the interaction and the scattering amplitude. You write it as a collection of some coefficients and some spin structures. And here are a list of spin structures. The A's are S over M. And then there's, of course, Levi-Civitas all over the place. And there's a collection of these spin structures. This is just the list for 1 power, 1 spin up to the 4th power. And if you just look at the known answers, it's actually a nice paper is the one from Newton through spin to the 4th. What you realize is there's certain guys are missing. The black ones here are missing. The blue ones are present. So you just conjecture. It must be true to all orders. Oh, sorry. Okay. Must be true to all orders. Oh, crap. Okay. Anyway, there's a spin so you can impose a shift symmetry on this in order to do that. Also, high energy behavior, you can impose that, and that's how we get the interactions. And this slide just says that, okay, you can apply that, and here's the answer for spin to the 5th. Now here's where the real fun starts. Starting at spin cubed, we have extra independent Wilson coefficients compared to the world line approach. So we're looking at a physical quantity, let's say a scattering angle. Then we have extra parameters. So what the heck's going on? And here's what I mean by extra parameters. I just mean extra Wilson coefficients. There's a world line. This is spin square. There's two spins there. And there's just one object they write down. We can write down 3 objects. And these are physically distinct, but you have to look at higher order in the spin. So these are spin square operators, but they affect spin cubed in the scattering. So we were wondering, what the heck's going on here? Anyway, we tracked it down, because the problem is there's 2 formalisms. The world line formalism, they have fewer Wilson coefficients than we do, but you can't discuss this if you're in 2 formalisms. You have to bring it to 1 formalism. So to bring it to 1 formalism, we said, let's go to E and M, much easier. In fact, this issue starts at 1 power spin, not 3 powers, so that's really good. And the idea is to just redo the world line, but now impose the SSC, the spin supplementary condition, only on the initial condition. The basic idea is you just look at the formalism. There's Steinhoff, there's Vines, and special thanks to Justin Vines, of course, for guiding Trevor through this. So Trevor did this calculation, 2 calculations. One, a Lagrange multiplier that imposes the SSC, and another calculation, you just cross out that term, repeat the calculation, and what you find is that indeed, on the world line, if you drop that Lagrange multiplier, you do have an extra Wilson coefficient matching what we find in the field theory. Also, if you can, with the extra Wilson coefficient, you can also match it to the previous result where the SSC was imposed. So I think we now understand what's going on here. And so basically, we've identified the source. We brought it to 1 formalism. And let me just emphasize, this issue is of basic importance. How many physical parameters describe spinning neutron stars? That seems like a very basic thing. And of course, there's more things that we need to do. For example, this check that we did to understand what exactly is going on was done in electromagnetism, not in gravity, so we should do it in gravity. And we are definitely looking forward to having some fun with our GR friends to resolve this. Okay, so the summary is scattering amplitudes give us new ways to think about problems of current interest in general relativity. We've pushed state of the art, the state of the art. There's G to the 4th conservative part that's complete. Conjecture for defining the Kerr black hole, order G square for the 2-body Hamiltonian. There's shift symmetry, good high energy behavior, and something a little bit puzzling, but I think we're well on our way to resolving it, is we find extra parameters, physical parameters, Wilson coefficients for describing generic spinning objects with gravitational fields. We've identified the source of the parameters on the world line, and I hope that it won't take too long to get a complete consensus on this. The final summary is that the amplitude approaches are pushing state-of-the-art in the post-Minkowskian framework, and they're providing new insight into physical questions. Okay, thank you.
Thanks a lot, Zvi. Time for a couple questions. Nope. Oh, there's a question in the back.
Thank you very much for this talk. You mentioned that you find some elliptic integrals, and you said that this is just a minor annoyance.
Yes.
Can you explain why this poses such a little problem?
Because Mathematica knows the elliptic integrals. So what you do is, Well, the differential equations are more complicated because you can't clean it up quite as well as you can if it's only polylogs, but you separate out that sector. And once you have a differential equation, one way or the other you can solve this. It's not a big deal. You know, once you understand enough about the basis of functions, you can also do series expansion. As we did it in our paper originally, we were too lazy to do it through a basis of functions, so we just worked out 500 terms in the series, and then, okay, then you have the answer. Then you can do a matching to the basic elliptic integrals, and it just worked. So that's a minor annoyance.
Ah, okay.
It didn't take very long once we got to the end.
Okay, thank you very much.
Can we expect elliptic polylogs at the next order?
Yeah, I don't know what we can expect, but as long as Mathematica knows it, I have no fear.
I don't know, does Mathematica know elliptic polylogs yet? Any other questions? Julio.
Hi, thanks for a nice talk, Zvi. So this idea of imposing or not the spin supplementary condition.
Right.
My understanding is that this was some sort of gauge fixing condition. Is
yes.
that not correct? Or because we wouldn't say this for Lorentz gauge,
not,
right?
Yeah, it's not exactly gauge fixing because, see, if you don't impose it and it was something like a gauge fixing at this level here, then you would not be able to solve it. You just wouldn't have enough equations. You'd run into a problem, but you do not run into a problem. And it's, you know, people say this SSC is like a gauge fixing, but it's more subtle, and definitely here it is not like a gauge fixing, precisely because it could be solved.
Okay, thanks.
Any other questions? If not, let's thank Zvi again for a great talk.
Oh, I have an announcement. If you don't mind. So there's a Nordita program in case you're hungry for travel. This wasn't enough. June 26th to July 1 in Stockholm. There's also a focus conference, July 24 to 28. That's just before Amplitudes, I believe. I don't know if it's, when is Amplitude? Maybe it's, when is Amplitudes next year? Maybe it's maybe there's a week gap.
Is August 7th to 11th.
Yeah, okay, there's a week gap. Okay, just in case you're from South America and you have students, there's going to be a great school. 2023, July 24 to August 4th. You may notice some overlap there. There's also overlap with the Amplitudes school that will be next year. But that's okay. It's in South America. That's very far away. I expect that this school will be full of South Americans, and the one here will be full of Europeans. So that shouldn't be a problem. And we're lining up great speakers. I have a quote from Nima. This school is going to be a blast. So if you know students in South America, make sure they know. If you have colleagues, friends in South America, please make sure they know to send their students. It will be a blast. Okay.
Okay, thanks. Time for coffee.
Okay. Welcome to the second session of Friday. It's my honor to introduce David Castlewer, talking about waveforms from amplitudes. Oh, waveform, you've changed your title. Waveforms and coherent states.
It is going to be waveforms from amplitudes, not from some other source. Before I start, I would like to express, as many other speakers have, my pleasure at being promoted from a little box on a Zoom screen to a live person with a live audience. It's really great to be back after 2 years in Zoomland, and also express my thanks to the organizers for putting this conference together. As many younger people don't appreciate, it's a huge amount of work and a lot of stress, and so thank you, Yara. Thank you, Carl. Also, before going on, I'd like to say that this is, or before launching in, this is work done in a collaboration with two very talented young physicists, Andrea Cristofoli and Ricardo Gonzo. Ricardo is actually in the audience, and both of them are at Edinburgh, as is my senior collaborator as well, Donald O'Connell, as I understand it, has recently been promoted to be a professor. So it's maybe I should have put an Edinburgh flag on this transparency as well. In any event, we've already had a beautiful introduction at the first talk from Alessandra Bonanno, and some of these points have been echoed by Tzvi, so I'm not going to belabor them. But the theorist's goal here is to enhance the detection and primarily the analysis of signals from gravitational wave events from current, but especially looking forward to future detectors. And these are, of course, going to be focused mostly on, ultimately on computing waveforms from the coalescence of compact objects, so binaries of compact objects, things like black holes, neutron stars, and maybe in some future dreams, white dwarfs, or perhaps exotic objects. So ultimately, we're interested in bound states and in perturbation theory, primarily in the in-spiral phase before the merger and then the ring down, which are currently treated either numerically or for the ring down through perturbation theory around typically black hole backgrounds. But we're not going to get there today. Today we're going to be focused on waveforms in unbound scattering, and to a large extent at the moment this is a theoretical exercise. But it is something that could conceivably be of observational interest at future observatories, and there's a long chain of ifs that have to be satisfied, that, for example, the origin of a lot of the black hole mergers have to be from the black holes clustered in the deep wells of globular clusters, and it has to be where scattering events suck energy out of these binaries in order to ultimately bring them close enough to merge. And maybe the world works that way, maybe it doesn't. So, of course, we're at amplitudes, and so I'm going to be applying quantum scattering amplitudes. So the first question you might ask, why quantum scattering amplitudes? Well, one answer might be that everyone loves amplitudes. Maybe it's not true outside these walls, but I'm sure that at least here, everyone loves amplitudes. But if we're going to be a little bit more down to earth, it allows us to focus on gauge invariant quantities, and that is at least somewhat simplifying a thing. The ultimate promise is that we can exploit the double copy and go from very complicated calculations in GR to simpler calculations in Yang-Mills and then sew them together. And of course, there's a whole other list of enhancements and technologies from quantum field theory that Tzvi has already discussed that I'm not going to replicate here. One other point that we're starting to see the glimmers of it. It's also very much in contrast to the way you do things in classical field theory, is that we can focus just on physical observables. We can focus on things that you actually can measure from infinity. You don't have to worry about computing things in the interior of the space-time. Now, the last few years have seen a flourishing of many new ideas and approaches, some of which are really purely amplitudes, some of which are kind of more on the periphery, some of which are applications of other ideas in quantum field theory. We've heard some from Zvi, we've heard some from Gabriele, and I think maybe I'm missing, yeah, we're going to hear some more from Michel Levy. I'm not going to have time to do anything more than flash this transparency. And instead, what I want to focus on are what I like to call the observables-based formalism, originally from a paper with Donal and his then graduate student Ben Mabey. And there have been other people. There's a beautiful paper by Julio, Mikhail Ruf, Mao Zhang, and Enrico Herman, which applied some of these ideas. And then well, I don't actually know what Chao Shen will be saying, but I assume he'll say a little bit about some of their use of this technology. And there are other people who have also started to dabble in it. So the idea here is to pick some well-defined observables in the quantum theory that are also relevant classically, and we express them in terms of scattering amplitudes in the quantum theory. And then we have to remember that even though everyone loves amplitudes and amplitudes are our friends, they're not directly physically observable in themselves. We have to turn them into observables. We have to do the right manipulations. And part of that involves understanding how to take the classical limit in an efficient way. So the basic setup is that we're going to scatter two things, and so we're going to shoot two things not directly at each other, otherwise these delicate Czech crystals will produce a very inelastic collision. We want something that's elastic up to radiation, so there'll be some impact parameter. And in the simplest case, if both of the objects are going to be massive, so if we're trying to model black holes or neutron stars, then we're going to start with massive scalars. Now, the examples of observables that we can think about would be the time-integrated change in momentum, which in classical field theory is called the impulse. We can think about the total radiated momentum, and we can think about the waveform of radiation, which is what we're ultimately interested in. And we'll see examples of the first and third of this list. And we're going to be doing just the plain perturbative expansion, so just the expansion in G. We don't need to rename it with fancy ways of confusing Pn and Pm. And we are going to be thinking about a conservative and radiation reaction really on the same footing. There's no particular need in this formalism to separate the two and think about them separately. Now, in conventional field theory, of course, let's say in the applications to the LHC, then we would be working with plane wave states. Here, we want to work with localized particles, and ultimately they want to be, in the classical limit, fully localized both in position and momenta. And so we build a wave function. We build the initial state as some integral over an on-shell phase space. In this case, let's say if we're doing two massive particles, we have two particles. We have on-shell positive energy delta functions. And then there's a wave function. There's a phase which is implementing the impact parameter. And then these are superpositions of plane wave states. And we can also, although I don't think I'll actually be making that much use of this more compact notation for the measure and the wave function. And a simple example you can keep in mind would be, actually there's a missing minus sign here, sorry about that. For the wave function is just a decaying exponential, and because we're dealing with a massive particle, this thing actually falls off. In fact, in the rest frame, this will give you a Gaussian. And there are various hats here which are hiding factors of 2 pi that we're otherwise too lazy to write out every time. So I'm not going to derive the impulse formula for you, but you can write down a formula which is valid to all orders. It has one term which is linear in the T matrix and one term which is quadratic. We call these with great originality I1 and I2. You can think of them as corresponding to the virtual and the cut terms. And the virtual terms start at order g squared, and the cut terms start at order g to the 4th. G here could be kind of any coupling. It could be the electromagnetic or the gravitational coupling, so either E or kappa. Now, when we're taking the classical limit, we have to take h bar to 0, so we cannot just take 1 to 0. We have to put the h bars back in. We do that by dimensional analysis, and it's possible to do that in a way that keeps a lot of the dimensions of states and amplitudes to be just what we think of them in the usual relativistic notation. Of course, we do keep c equals 1 because we're doing everything relativistically. There are 2 places that h bar can come in, either through the couplings or through the messenger momenta, because the messengers here collectively referring to photons and gravitons, and if we had any massless scalars, we would refer to them as messengers as well, that for the massive particles, the basic strategy or the basic lesson is that you should just keep them in terms of momenta. For the messengers, you should think in terms of wave numbers, and that introduces extra factors of h bar. So the basic way we evaluate things is we take an observable, we substitute in that wave function that I showed you, we make h bar explicit, and then we evaluate the matrix elements for whatever observable it is that we have, and now we turn the crank. In general, we have to Laurent expand in h bar. There can be individual contributions which are singular. This doesn't happen at leading order, but does happen starting at next to leading order. In physical observables, these singular terms will cancel. When we turn the crank here, which sometimes I may denote by these double angle brackets, the wave functions will basically turn into simple objects. We'll end up replacing the massive particle momenta by the mass times the 4 velocity. And then we'll typically be left with some simple integration over some sort of phase space left over. And that will be an integration that would also show up in a corresponding classical calculation, although not always in the same way. And the other thing just to keep in mind as we're taking the classical limit is that we have kind of 3 scales to be thinking about. There's the Compton wavelength of our massive particle. There's the kind of size of the wave function that we've built, so it might be a minimum uncertainty Gaussian wave function if we're thinking about the non-relativistic limit. And finally, there's a scattering length, which turns out to be essentially the same as the impact parameter. And we want the particles to be localized. We want the wave packets to be very well separated so that they're not peering into each other and we're not starting to see either quantum or width effects. If we did have objects that were not just point particles, then we would end up introducing higher dimension operators, which are kind of capturing the ability of one of them to peer into the other through the interactions. And you can do a more careful analysis to confirm what we call this Goldilocks condition, this double, where you need 2 ratios to be much smaller than 1. So I'm not going to go through a full example of the impulse for massive scattering. You can look it up in some of our old papers. But I do want to ask another question, which is what happens if you want to scatter not just massive objects, but massless objects? So there seem to be some kind of line 1 problems. First of all, the Compton wavelength is essentially infinite, so it's impossible to satisfy this Goldilocks condition for taking the classical limit. On the other hand, it's clear again that plane waves are still not appropriate. And so the solution is to use something which the quantum optics people have been using for a long time, which are coherent states. And so the coherent state is something that's built through an exponential of a creation operator. And this is going to create a state of where the number of messengers, the number of photons, or the number of gravitons is indefinite. And the states are then eigenstates of the creation operator, so that then satisfy, so if you act with a creation or an annihilation operator of the appropriate helicity, you'll pull down a factor of this function alpha, and this function is a C-number function. It could be complex, although it's generally more convenient to take it to be real, multiplies inside the exponential the creation operator, and it's something we call the wave shape. And choosing that function is the way you ultimately choose what kind of classical wave you're going to have. Because even though there's really only one kind of spinless point particle, there are many kinds of classical waves, and we need to be able to accommodate them all. So what is the connection to classical fields? Well, we can write down the operator, let's say the electromagnetic field operator, in terms of annihilation and creation operators. And of course, there's polarization vectors that dress it, and there's a factor of h bar to get the normalization correct. And let's compute its expectation value in our coherent state. And what we find after a certain rescaling is that we get a formula that corresponds to the mode expansion of the free classical field. So we have what are the Fourier coefficients, which are now alpha bar as a function of k bar. K bar is exactly the wave number that I defined a little while ago, so the momentum divided by h bar. What are these Fourier coefficients? Well, we have to rescale our wave shape function by appropriate powers of h bar, and that gives us the classical Fourier coefficients. So this now gives us a classical wave. So as long as we choose the wave shape appropriately, we can use a coherent state as our initial state, and that will give us a classical wave coming in. So one of the things that distinguishes these classical waves from just an ordinary plane wave state is that the number of photons, we can evaluate that. We just put in the number operator, and we find that when we re-express it in terms of these classical Fourier coefficients, so here there's no h bars. We have an explicit 1 over h bar in front. And so this number should be large. A classical wave essentially is a coherent state with a very large occupation number. And that will be true so long as alpha bar is not parametrically small when h bar goes to 0. So that's one of the constraints. We have to choose alpha bar in such a way. And the simplest way to do it is, of course, to choose alpha so that alpha bar is independent of h bar. So the initial state now, if we're looking at, for example, scattering a classical wave off of some point particle, is going to be very similar to the two massive particle initial state. We're going to have one integration over the massive particle on-shell phase space, the wave function, the impact parameter if we choose one, and then this initial state, which is a cross product of a plane wave state and a coherent state. The impulse formula is, of course, the same, except that we put in this initial state in. There's two terms. And at lowest order, the only thing we need is the first term. So we simply write out phi w here on both sides. And again, there's vestiges here. It's more like an in formalism. These are not an initial and a final state. These are different copies of the initial state. And now we have to turn the crank. As I explained earlier, we need to evaluate this matrix element. Now, if these were just two massive plane wave states, everyone knows how to do that. It's something you learn in your first week. Well, maybe not your first week of quantum field theory course, but definitely your first week of an Amplitudes course. But here it's a little bit more subtle, so it's worth spending a couple minutes. These are not of definite order in perturbation theory, and so you'd ordinarily introduce a complete set of states on both sides, and then you'd compute all the matrix elements, and then you'd resum them. And this is complicated because there's many disconnected pieces, and so you can do it, but it's tedious. And instead, it's better to go back to one of the greats of 20th century physics and look for a different representation of the transition matrix, where you write it out in terms of matrix elements on definite particle states times creation and annihilation operators, and I'm just writing the lowest order terms here. There's, of course, an infinite set of terms here. And now you plug in this representation of the T matrix, and you find kind of conventional delta functions for the massive particles. And the thing that's a little bit different is you find these normalization factors, these wave shape factors for the coherent states that otherwise you'd have to reconstruct by doing very complicated sums over the disconnected pieces. And the thing that multiplies it is otherwise a very conventional amplitude. So one of the applications is you can reproduce the light deflection. That just corresponds to doing gravitational scattering of a photon. So it's a 4-point amplitude, graviton exchange between the photon and the massive particle line. And you want to choose within the classical regime the geometric optics approximation. You do that by choosing a certain wave shape, and there are certain restrictions on the wavelength of light and on the transverse size of the beam. And those are choices you can make rather than things that are imposed on you. And when you do that, not to anyone's great surprise, I'm sure you reproduce the well-known value. So I'm running a little bit short. I will probably exercise the chairman's patience a little bit. But I do want to go quickly through the derivation of waveforms. So the impulse is, in a sense, a global observable. You have to decorate the entire celestial sphere at infinity with detectors to be able to measure it, because you don't know where the particle is going to go. But there are observables which are more realistic. These are local observables where you just look in some place, either for photons with maybe the Mark I eyeball, or for gravitational waves of a very sophisticated multi-billion-dollar laser interferometer. So you have some scattering that happens in some region, and there's some radiation that propagates in that direction. You can think of this scattering region as creating kind of like a current, and you can then write a radiation observable through the propagation of that current. And the leading large distance behavior is the waveform, and all the other things that are suppressed by 1 over x squared or so are simply going to die off. So let's look in the electromagnetic theory. We're looking at the expectation value of f mu nu. So we write, again, f mu nu now in the out state. We write the out state in terms of the evolution operator here, the S matrix thought of the evolution operator on the in state. And that fits into our general form where the current now has an explicit expression. This would be the initial state that I wrote on an earlier transparency, the S matrix, and just here this an annihilation operator. The complex conjugate would have a creation operator. So people who like spinors should like the Newman-Penrose formalism, which is a very nice way of writing things down. It's a spinorial way, and we can write down then in electromagnetism, it's the second Newman-Penrose scalar that's relevant, and we can write down essentially a frequency integral expression for it in terms of things that are very closely related to this current, but now where the creation and annihilation operators have definite helicity. So we can do this at leading order in electromagnetism. It's convenient to rewrite the formula in terms of the S matrix on the previous line, and again in terms of two terms, linear in the T matrix and quadratic. And this one has, you can make the reality manifest here. The reality is manifest anyway. Now we simply plug in our expression for the initial state at leading order, again, we only get this term, which starts at g cubed. This one would start at g to the 5th. Since we're now doing scattering of massive charged objects, there's now more integrations over the massive particles. There's two copies, the in-state and its conjugate. And we get a matrix element now between plane wave states, so we don't have to worry about coherent states because there's no radiation in the initial state. And there's an additional annihilation operator, which creates an additional photon, in this case, in the bra. And that then just gives us a very conventional 5-point amplitude. You can rewrite the object you get in terms of the same radiation kernel that shows up in the calculation of the total radiated energy. And you can either rewrite the expectation value for F mu nu, and in terms of this radiation kernel, and then a phase space integral over the emitted radiation. Or equivalently, you can write it for the Newman-Penrose scalar directly, and that just tells you essentially you have to take the classical limit essentially of the radiation kernel. So the radiation kernel is a surviving integral, one surviving integration over what we call a momentum mismatch. From the point of view of the amplitude, you can think of it as a momentum transfer. So that's the vestige of the phase space integral at leading order. So the building blocks, if you actually work it out explicitly, are Bessel functions in frequency space. In the gravitational case, they'd be one-dimensional integrals over weighted Bessel functions, but basically the same kind of animal. And you get waveforms in the electromagnetic case, which again have this spinorial expression. So there's a direction vector, which is 1 n hat, and you can build spinners out of that. And then in terms of the four velocities of the two particles and the 4 vector, which characterizes the impact parameter, and these various Bessel-like functions, you can write down relatively compact expressions. The analogous calculation for gravity will involve taking an expectation of the Riemann tensor, which at large distance will be essentially equivalent to the Weil tensor. And again, in this case, it's the 4th Newman-Penrose scalar, and the integrals are not the same. They're slightly more complicated integrals, but the structure will be that you can kind of see a double copy structure in the spinorial prefactors. So I see actually that I was somehow thinking that I had a little bit less time than I did, so I guess I'll actually make the chairman happy and put up my summary slide here. So I've tried to give you a little bit of a snapshot of the observables-based formalism, and where you take observables, where you can start by defining them in the quantum theory, and these are necessarily then observables that you can express at infinity, at least if you want to work in an on-shell way. And you then introduce the h-bars from dimensional analysis and momenta for massive particles, wave numbers for massless particles, and the classical waves that you'd be scattering correspond to coherent states with your choice of wave shape function. And the other kind of basic message is that the waveform that you're ultimately trying to calculate is basically a 5-point amplitude. So let me stop here, and there will be a couple more announcements, but let's do questions first.
Thank David for the lucid talk. Questions now. Lance?
Thank you. Nice talk. One place where your formalism might be useful is in the one-loop quantum corrections to the deflection of a massless particle, like a photon or a graviton, by a gravitational source. Because when you do it with just plane waves, you get in dim reg, a 1 over epsilon pole. So there's some obvious dependence on the experimental setup. I wonder if you've looked at that.
We haven't, mostly because my prejudice is that quantum effects are going to be unobservable, and I'd like to focus on observable things first. But yes, in principle, I have, for example, a colleague, actually 2 colleagues at the moment, Josef Benna and Nick Werner, who believe that large black holes will have a very significant quantum hair. And if you believe that, if you believe there's some essentially dimensionless constant that magnifies the effective quantum effects, yeah, you can systematically work to higher order in H bar if you feel like doing that. And yeah, I mean, I actually wasn't aware of this conundrum, so it might be something worth looking at. Julio.
Thanks for a nice talk, David. So, this waveform, the phase of the waveform is known to be infrared divergent, and this is just the uncertainty in the initial phase, where, like, you don't know when the thing was produced, and so I was wondering if, because infrared divergences, we expect them to be of purely classical origin in this case, if this exponential representation of the S matrix makes it easier to analyze, or if this formalism in general, you could just predict where the infrared divergences will come in, and
probably, but we haven't really looked at. I mean, this is something you're going to see at higher order, and we haven't done any higher order calculations yet. Although, if you come back and ask me next year, I think that whole situation will have changed.
Okay, great, thanks.
I mean, it's not exactly the question you asked, but there's also kind of a related open question, which is to prove for generic observables, or maybe more less ambitiously for a specific set of observables, that the 1 over h bars that arise in intermediate stages cancel out of physical observables. There should be some analog of the KLN, the Kinoshita-Lee-Nauenberg theorem, and that's something I keep saying, but I don't know how to do yet. And maybe that, I mean, the 2 issues are connected, so, yeah.
Maybe I ask a short question. In the coherent state story, the coherent states, the factors scale with h bar, so this is a new source of h bar counting. Is it really an issue when you go forward? And
so the h bar analysis in the amplitudes and in the kind of turning the crank is different for the massless, massive, and massive, massive case. Mm-hmm. No question about that. In a certain sense, you can think of it as I'm choosing alpha bar rather than choosing alpha, even though it's not the way it works in the quantum theory. And when you do it in kind of the most naive way, there's no additional...
It's just overall factors.
It's just overall factors,
okay. Yeah. Thank you. Well, let's thank David again.
And now, can we put the transparencies back up? And okay, so now I will redo the talk at lightning speed. Although, actually, are you able to just skip to the end of the? Can you just skip just to the summary slide? Yeah, a little bit faster than. Okay. Yes. Yeah. So there are actually 2 conferences or 1 conference and 1 workshop. So yeah, let me go on to that. No, it's fine. It's fine. So one is not for next summer, but already for this winter, there will be an edition of QCD Meets Gravity in person, unless the world falls apart. That will be held at the University of Zurich, and it will be at kind of the conventional time between the 16th and the 12th and 16th of December this year. And the other thing is a workshop, which is kind of a partner to the school that Zvi announced. It will also be held at the ICTP in Sao Paulo. And again, certainly for those people who are in the audience who are from Latin America, and whether or not they're at Latin American institutions is not important. And to some extent, if you know people who are not here and are from Latin America, you should definitely let them know about that. It's not restricted to people from Latin America, but obviously we're going to try and get you know, a high weight of people from Latin America. That's the purpose of SAFER. And so this will be separated from the school by the Amplitudes conference. So those of you from Europe who want to attend everything will be bouncing back and forth, NEMA style, across the Atlantic. Just go ahead.
Now it is a great pleasure to welcome Xiaoshen Shen's talk on amplitudes, angular momentum, and the binary spiral problem. Take it away.
Okay, so first of all, I'd like to thank the organizers for this beautiful conference, as well as the invitation to speak. So today, I will talk about this paper with Anish Manohar and Ella Ridgway, both from UC San Diego. So I'd like to begin with the following question. So can we solve the full binary in-spiral problem? In particular, can we use QFT methods to solve this problem to a precision that's very hard to imagine from the traditional method? Okay, so in the past few years, as we learned from other talks already, there has been tremendous progress in the so-called two-body problem, in particular in the conservative sector. So here, the binaries, they have these nice circular orbits, and the information is encoded inside this effective potential for effective field theory. And the reason that we made so much progress in the past few years is that if we consider the analogous scattering states, then from the initial and final states, we have Lorentz invariance, which implies that the physical observables are the 4-point scattering amplitude in terms of magnitude stand T and S, or classically, you can map this to the scattering angle in terms of the angular momentum and initial energy. So this immediately implies that the effective potential should only have 2 degrees of freedom. So this eliminates this extra gauge redundancy. And on top of that, because of the Lorentz invariance, we know the results are nicely written in terms of the relativistic Mendelssohn. So the results are a simpler function in these variables instead of the more naive swing momentum in effective potential. So that's the reason why we can bring together this scattering amplitudes and effective field theory to make a lot of progress in this two-body problem. However, as we learned from Alessandro earlier today, that there's another important aspect of binary in-spiral, which is dissipative dynamics. And it's encoded in the so-called radiation reaction force, because as the gravitational radiation carry away energy and angular momentum, the two binaries spiral into one another. So this force effectively looks like a friction, and it's actually first calculated by Burke and Thorne more than 50 years ago. And it's not a small effect, because this already started at 2.5 post-Newtonian order at level of equations of motion. And 50 years afterwards, we only have partial understanding up to this 4.5 pn in the post-Newtonian expansion. So as summarized by this plot here, that we only know this shady area in terms of velocity and G expansion. So I would like to make progress on this direction. So how should we proceed? So just like the conservative case, we also want to explore symmetry. And the point here is we can simply live from Lorentz invariance to Poincare invariance. And what Poincare invariance tells us is that
total energy and angular momentum are conserved. So as the radiation carry away energy and angular momentum, these back react to the matter system. And from these two observables, we can simply use classical equations of motion to solve the two components of this radiation reaction force. So here, I only consider binaries without spin, so all the motions are on a plane. So now the question now boils down to how do we calculate these Poincare charges. And in a very nice paper before us, this radiated energy has already been computed by these authors. So in the following talk, I'll focus on calculated this angular momentum. And together with the effective field theory, we'll be able to recover this entire G squared and G cubed radiation reaction force, which is what Alessandra asked earlier today. So now let me focus on radiated angular momentum. So of course, angular momentum is a basic observable in a gravitational wave event. So there's a well-known formula if you just open the textbook. So this is a formula, and the details are not very important here, but I just want to emphasize that it's a formula in terms of this metric. So it's a so-called transverse stressless part of the metric. And this formula gives us the spatial part of the angular momentum. But as we know, that angular momentum is really a rank 2 tensor in the relativistic theory, so you can immediately ask two questions. So why can't we have a covariant formula for angular momentum? And on top of that, this TT projection of the metric by itself is really gauge dependent. So only observables are gauge invariant. So is there a way we can see the gauge invariance in a more manifest way? Okay, so now let's go back to the basic. So if we consider a scattering event like this one, so in the final state, the linear and angular momentum, these are total conserved charges from Poincare, and they're given by integrating over the stress energy tensor over the entire space. So for angular momentum, we have this additional x, and this is the analog of r cross p in classical mechanics. And as we will see, this additional x is very crucial, and in particular, that means that we have to go to subleading order in the large R expansion. So in our approach, we'll simply start with the sources. From here, we can solve the fields like the metric or the gauge field. From here, and we'll get the stress energy tensor, and finally, integrate over the entire space, we'll get the linear and angular momentum in terms of these sources. Okay, so let me start with sources, and I'll consider both GR and E and M. So in the case of E and M, these are the typical currents, and of shell, there are actually 3 degrees of freedom because the only condition we can impose is current conservation. So only when we go to on-shell, then we have residual gauge freedom to project this to the usual 2 degrees of freedom. And in the case of gravity, so we have the analogous stress energy pseudo tensor, which include both the matter contribution from the first 2 diagrams, and here the straight lines here are matter, the wavy lines are gravitons, but also it also includes this self-interaction from gravity. And just like E and M, there are actually 6 degrees of freedom of shell because it's only constrained by stress energy conservation. And only when you go on shell, then it reduces to 2 degrees of freedom after this transverse and stressless projection. Okay, so once we have the sources, we can easily solve the fields by classical equations of motion. So for instance, if you pick a Lorentz gauge, then in E and M, we have these nice equations of motion for the gauge field. So then you can solve this when you convert the current with retarded Green's function. And then you can solve the entire field after gauge fixing, even for the static sources. So in terms of position space, the gauge field now looks like the following. So we'll use the same large R expansion that's also mentioned in David's talk. The leading 1 over R part in Lorentz gauge have this nice form. And you can have a residual gauge redundancy to move this into 2 degrees of freedom, which is related to the usual amplitudes. However, when you go to R squared, it's in general not just 2 degrees of freedom. And just to give a sharp example, the Coulomb field we learned in high school, the electric field from the static charge, it's actually started at only 1 of R squared, but it's radial, so it's not a transverse electric field. So that's why in terms of solving these fields, we like to use these sources. And once we have these fields, then we can, a nice way to package this is to go to momentum space. So here we integrate over the phase space, and this mode expansion are the sources in momentum space. Okay, so once we have the fields, then we can go to stress energy tensor. So far, EM and gravity, they're more or less the same. The only difference is in terms of stress energy tensor, where in EM we have gauge invariant T nu nu, and it's well known in gravity that local T nu nu is not gauge invariant, but when we compute the global charges like linear and angular momentum, then we expect that these results, final results, are gauge invariant. Okay, so as a warm-up, then we can just go through this pipeline. So we started with the sources. We can go through this pipeline all the way to the final answer to the linear and angular momentum. So as a warm-up, we can look at the linear momentum. And it turned out that from this first principle derivation, results agree with our naive expectation, which are this linear momentum is basically integrating over the phase space. You take the cross-section, return in terms of these sources. These are the spin 1 and spin 2 polarization sum. And they're weighted by this momentum insertion, this K mu here. And this formula, they're manifestly covariant, and the gauge invariance is also very easy to see. And you can directly relate it to onshore amplitudes using the KMOC formalism that David just introduced. But now, using exactly the same pipeline, we can study angular momentum. So from this pipeline, then we obtain a new formula for angular momentum that's covariant. And just like the linear momentum, P mu here, it's also a quadratic function in terms of these sources. And this L nu nu here is a differential operator written here, and sometimes it's also called orbital angular momentum operator. And we also have this additional piece. So how do we know this formula is actually correct? So we can use this consistency test. So first thing is that we want to obey Poincare algebra. And Poincare algebra says that if you have a translation, angular momentum is actually not invariant, but there's a part that is covariant and is proportional to linear momentum. So that's the reason why the first two terms here, they have the very similar structure as the linear momentum, because under a shift, you pick up a constant piece from the first two terms, and therefore it has to have the same structure as the linear momentum. And second, we also want to check gauge invariance. Term by term here in angular momentum is actually not gauge invariant. In particular, the first term and the last term, they are separately gauge dependent, but only this particular combination give you gauge invariant results. So another way to say that is that sometimes it's called orbital and spin part of the angular momentum, but this separation is actually not physical, only the combination is gauge invariant. Okay, so once we have this formula, so now we can consider some simple examples. So let me first consider the zero frequency limit, which is actually sufficient to get the leading order result. And this zero frequency limit is also the so-called one-Byrne self-theorem or memory effect in GR. So using this zero frequency limit, which basically means that we zoom out the time scale such that the scattering becomes like this configuration with some free initial particle and a kink at t equal to 0, and then the particle fly out again. So we have the stress energy tensor coming from this initial free particle. So in momentum space, this gives you a delta function in the frequency. And from this kink, which is the theta function in time in Persian space, so when you Fourier transform, it gives you this 1 over omega plus I epsilon in frequency space. And as known famously from Weinberg, the result here is valid for any deflection. And it's given by diagrams like this type. Okay, so now we simply plug in this formula, this straightforward tensor into our formula. So if you plug in this, unsurprisingly, the linear momentum is actually 0 because here we have 0 energy mode. However, for angular momentum, because we don't have the additional k mu, the momentum insertion, so it turns out that we actually get a finite result for angular momentum. So this looks very peculiar because if you think about how to detect this effect from a detector, the detector looks like cannot measure any energy, but still with some finite angular momentum. But you really have to think about this as a large R expansion because angular momentum is R cross P. So even though the momentum is infinitesimal in 1 over R, but since you have a large R, so overall, this can still give you a finite result in angular momentum. So there's nothing wrong for this effect. So now, taking the leading order in this deflection angle, the loss of angular momentum, the ratio, can be written in terms of this nice formula, first found by Damore. So this formula, these are just simple logs from the kinematic invariant. And one important thing for this formula is that this is actually model independent. So all the scattering information is encoded inside this theta. And there's a sharp distinction from radiated energy. So the angular momentum doesn't have to be positive. In fact, this leading order is 1-to-1 correspond to the sign of the scattering angle. So it's only positive when the scattering is attractive. Okay, so in principle, if you go on to higher orders, you should worry about IR divergence. Because from this soft analysis, we know each of them can scale as 1 over omega. And when you combine with the phase space, you can see that there's a log divergence in this energy integration. However, we know exactly what the divergence should look like because it's dictated by Weinberg's soft theorem. So this is a trivial integration. You just integrate over the 4 pi solid angle, but it turns out all these log divergence, they cancel. So this implies that the total radiated angular momentum is actually finite in soft limit. And this also applies to EM, GR, and scalar radiation. So now, using our formula, we can compare with other known results in the literature. So we agree with other results at order G squared, and fully agree with very nice paper by De Vecchia, Carlos, and Rafael Russo appear soon after our paper. But there's a sharp disagreement with the textbook formula I showed earlier in the initial rest frame by a factor of 2. Okay, so let me dive into this. So then be just super concrete. So at leading order, order G squared, the loss of angular momentum can be calculated using these two formulas. The textbook one is written in terms of the transverse power of the metric. And both of the textbook and our formula written in terms of the sources, we agree in the center mass frame. However, if we go to the initial rest frame, there's a factor of 2 difference. So we want to analyze this difference. We want to use other independent analysis. So first one, we'll use general covariance, and the second one, we'll use the known radiation reaction force in GR, derived by other people. So the first thing is, because we know angular momentum is a rank 2 tensor, so we can parameterize that using the known vectors in this problem, momentum P1, P2, and the 2 impact parameters. And one crucial ingredient is that we have Poincaré invariance, Poincaré algebra. So it means that this B bar, which is the average of the impact parameter, will shift under translation. And therefore, the corresponding coefficient has to be exactly the linear momentum. So here the F1, 2, 3, where G1, G2 are these H1, 2. These are form factors. They are just arbitrary function of the kinematic invariance. These are the same form factors that we use in nuclear physics. And from this general covariance, then we can go to the soft limit, which basically means that we set this F1, 2, 3 to 0. And then we can compare the general result in center mass frame and rest frame without any perturbative expansion. And the ratio in center mass frame is given by the form factors G1 plus G2, and rest frame is just given by G2. And these two functions, they're related by 1-2 symmetry. And at leading order, on G1 equals to G2. So it implies that there's a factor of 2 difference between the center mass frame and the initial rest frame. Okay, so our answer agrees with this general covariance. And the second thing is that we can take the known perturbative data calculated by Byrne and Sohn more than 50 years ago. In particular, it says that the acceleration from this radiation effect should be equal and opposite between the two material particles. So you can just plug into scattering initial states, and you'll find this is the effect from radiation after scattering. So as you can see, the initial and final energies, they're the same. So that means you don't lose any energy. But the effect of radiation is simply to shift this impact parameter by equal and exactly the same between the two particles. This is actually very surprising from a Newtonian world, because that means that even though this could be a supermassive black hole in the center of our galaxy, the other one can be just a tiny baseball, and yet the radiation effect, they shift exactly the same amount. So the heavy particle doesn't decouple, and this is similar to like heavy top quark, because Yukawa coupling is also very strong, so it doesn't decouple. So now we can simply use this as an input to analyze the issue. And because that the impact parameter will shrink equal and opposite between the two particles, so in the center mass frame, because both of them are moving, so it means that you lose 2 units of angular momentum. But in the rest frame, because this particle doesn't move, so that means you only lose by 1 angular momentum by 1 unit. And as let me emphasize again that the back reaction on this heavy particle is really important to get this effect correctly. So we conclude that using the general covariance analysis and Byrne-Sohn radiation reaction force, our formula agree with these two general analyses. The standard formula, while it's correct for bound orbits, and on the other hand, for scattering, even at leading order, is actually incomplete because of the presence of these soft modes. So, okay, now after we understand these conceptual issues, we can go to the precision frontier. So now we'll move on to order G cube. So it's very, the calculation is already more or less straightforward now. So the energy part has been calculated again by this very nice paper from these authors. And the angular momentum part have both the zero and finite energy contribution. The zero energy part is very similar to what I just described. We just need to plug in the next to leading order impulse calculated from the 80s. So this finite energy part is given by a diagram that looks like this. And thanks to these authors, we know the spatial function, so we can simply resum the velocity expansion, although there's a very nice progress from this poster by Carlos. And the final answer can be compactly written in terms of this table. Here, these are just some simple functions of ordinary logs, so these are trivial for audience in this conference. And when we do velocity expansions, the first 3 orders agree with the earlier paper by Bini, Damore, and Girardico from last year. And, but we complete the rest to orders. So these complete this G square and G cube in these radiated charges. So as the first application, we can look at the G through a force impulse that's R in velocity. So impulses can be separated into the conservative part and the dissipative part which can be first separated into even or odd in time reversal. So the part that we complete is this third coefficient, and we also calculated the conservative part with some other people. So the only missing piece now is this dissipated part, but even in velocity. And once I want to emphasize here that the calculation is really straightforward thanks to this beautiful formula by Byrne and Damour. Essentially, this factorizes the perturbative order into these conserved charges and the conservative part. So for G to a force, we really just have to start with mostly leading order inputs in the calculation. So back to the initial question I asked in the very beginning. So we want to solve the binary inseparable problem. In the equation of motion, we have the usual conservative part discussed by Zvi and others that we can extract from scattering angle, now up to G to a force orders in velocity. And for the dissipated part, now using this energy and angular momentum, we can bootstrap to orders in V at order G cubed. So these are just honest equation of motion. Now we can plug into Mathematica and solve numerically. So as you can see, the blue dot here is the one from conservative part, so it's perfect circular orbit. The red one on the right hand includes this dissipative effect. So it has this in-spiral trajectory. And the physical information is encoded in the change of this energy and angular momentum over time. So now back to the phonological application. So far, this plot only includes the conservative calculation from first principle calculation. So it will be very interesting to see the effect of this dissipative part. And that's something that professional people like Alessandro will be able to answer. So I'm running out of time, so let me just summarize. So once again, symmetries are proven to be very powerful. And we can bootstrap state-of-art dissipative force in GR purely from scattering in Yang-mills. And along the way, we found new formula and perturbative data and non-perturbative structures for angular momentum. So in terms of future work, one obvious thing is to go to higher orders. We should be able to see interesting functions like actual polylogs, elliptic functions, and that's the next order will be the first time that we'll be able to see tail effect. And as you can see, that angular momentum is really helpful for gravitational waves. So in particle physics, you can also ask, like, what are the questions that angular momentum would be a good answer? So I'll start here. Thank you.
Yeah, thanks, Xiaoshen. Questions? Julio first. Yeah, okay, Julio first.
Thanks for a great talk and presenting this amazing work. Can you go to the slide about the finiteness to all orders? Okay, so here you prove that the phase space integration doesn't introduce additional infrared divergences. But as we were discussing after David's talk, the waveform itself is known to have infrared divergences in the phase. So how do we see from this argument that those don't end up in the final result?
Yeah, so here I only show that the soft divergence part will be canceled. So the part you mentioned, that could appear in this additional divergence in these sources by itself. That part, I don't have a definite answer. Although my understanding for that type of IRL divergence is that it will cancel in terms of cross-section. So between like T star and T, but I don't know exactly for sure.
That is true in the energy loss because you just have the absolute value squared. But here, because you're taking a derivative, if the derivative hits the phase, it's unclear.
I totally agree.
Okay.
Yeah, I don't know.
Hi, Session. Thanks for a nice talk. Just one question, like, does it have application for some rules in QCD, this new expression for the angular momentum? I know that there were a lot of problems like in understanding orbital and spinning angular momentum in QCD and some rules, and you have these nice form factor decompositions in terms of symmetries.
It could be, I don't know. It could be that, for example, given that you have a decay of a, say, mass with certain spin, maybe this will constrain the final state because you know the final spin cannot be greater than the initial. So maybe, but I don't know. Yeah, that's an interesting question.
Okay, thanks.
Lance here.
That was great. If you add spin to the picture and it's not a line spin, I guess it gets more complicated because now the angular momentum that's radiated can also be in all three components instead of just one. And maybe you have to share between orbital spin and radiation at the same time. Have you thought all about that?
Thank you.
Yeah, so discuss with other people like Gustav a little bit. So yeah, indeed, this is a great question. So in terms of equation of motion, so here, because there's no spin, so it's only like position and momentum. But with spin, then you have additional equation of motion for the spin. And so first, the radiation reaction is now not just like two component because it's a three-dimensional motion. And you also want to add radiation reaction effect for the spin change. So in that case, I don't think having the radiation itself is sufficient. You will also need to calculate what's the final state spin in order to bootstrap the full equation of motion.
We have a question from Zoom. Riccardo Storani is asking, what can you compute at order g to the fourth? Can you compute the energy radiated at order g to the fourth or just the angular momentum?
So I think the formula is already out there. So if we turn on the crank, then I believe sooner or later, maybe next year, that somebody will calculate the radiated energy and angular momentum. So yeah, now it should be straightforward. Maybe then we'll see interesting issues like divergence. That will be an interesting place to analyze these divergence or tail effect. Although I should say, yeah, maybe Ricardo is asking, so one thing about tail effect, this is also the same effect that Zvi mentioned, that the equation of motion is no longer local, and we will have exactly the same issue as the conservative part. We would need to put in more work in order to convert the scattering result into bound states.
Okay. Great. Let's thank Xiaoshen again. And the next speaker is Michelle Levy. I'm happy to announce her talk on Tale of Tales and via generalized unitarity, and this is on Zoom.
Thank you, Alex. So first of all, I want to show you my copy of the Soldier Schweik, because I was fantasizing on coming to Prague and doing some tour sites of Soldier Schweik, my all-time favorite book, but I couldn't, so I'm very sorry that I couldn't join you. Do you see my screen? Do you hear me?
Yes, we can hear you. Great.
Okay, okay. Move to presentation. Okay. So firstly, I want to say that I'm presenting the work that was created together with Alex Edison, who I understand already left. On the back of this bunny, there is a portal to the preprint that includes more details probably than what I will be able to cover. So first of all, I want to tell you what we are after, what we sought to find in this goal of ours, in this project, which is in general opening a line of research. And as most of the people know, I come from the point of view of EFT. And in particular, I'm interested to capture effects which are more advanced already in terms of the evolution of binary dynamics. There are graphs here that describe the binary in a representation where these vertical lines are the world lines, and they are emitting radiations from the system. And the point is to represent to you pictorially that if we zoom out of this EFT, and we go up to another level, we increase the scale, We are now talking about an EFT of one single word line of a single composite particle of the binary, which is emitting radiation. It has a set of multiples that characterize it, which have some microphysics going on in them that we don't know. And in particular, what we want in general, what we wanted to do in general in this project is basically to open the window to describe all hereditary effects, which means any scattering of radiation from the binary of its own gravitational background. It's in the case of the tail of tails, in the case of tails, this is really like the simplest prototype of this kind of scattering, in the sense that this is scattering of the leading source of radiation from the leading multiple of the binary. Just for orientation, for those who don't know, like the post-Newtonian world and the precision frontier and stuff, the radiation reaction, which is just the fact that if the system radiates and the part of this radiation background affects back the word line of the binary, it starts at 2.5 pn, where this is the notation of a pn. However, the scattering, as you can see in these diagrams, it started at 4 pn. So, and it's also different in the sense that while this is only an effect that comes from a radiation, and you will see it also, the effective action looks differently, and it's just different. What involves already the scattering already entangles both the conservative dynamics and the dissipative observables. So it will exert forces on the individual components of the binary. It will affect the binding energy of the binary on the one hand, and on the other hand, it will also, we will also see it in the flux, in the power spectra of the binary. And so in general, we want to be able to capture all of that. And one can essentially also, as you can see here in these figures, kind of think about it in kind of 2 points of view. Firstly, that we just have something which is on shell radiating, and there is some observer here at infinity, asymptotic infinity, and we're just like trying to compute correctly what is this like 1-point function. That's like one possible point of view. But if we will only do that, we won't get information, for example, on what happens back with the effect on the binary. So this is what we call the radiation reaction point of view. So there will be some ambiguity in this talk in the sense that I will, usually we call the leading effect radiation reaction, but also in general, all this family of effects that come afterwards. So in the radiation reaction point of view, we're interested to examine in general everything that happens to the binary, as I said, conservative and dissipative. So there were great giants that came before us that are still here and have been treating this, this problem for many decades in a very impressive way, and really left us an abundant trail of results to follow and to try to build on. So they should get the credit that they deserve. In particular, the first paper that addressed such a scattering of radiation appeared in 1988 with Blanchet de Moore, but going forward, essentially Luc Blanchet was the one who really carried the progress along this line of all these type of effects. Along the years, with his various changing collaborators, essentially students and postdocs, and it's all captured in his living review, very seminal review in post-Newtonian theory, the last release of which is in 2014. And the latest milestone that came from this school of thought was to reach what we call the tail of tail of tail. So a triple scattering that you will see represented later. And this was achieved quite recently, I would say. I mean, in terms of these timescales, it was achieved with Luc and students and postdocs in 2016. You can look at this very nice preprint. It computed the dissipation at what we call plus 4.5, because once we are starting to talk about effects that are entangled with radiation, we want to count them beyond the leading radiation reaction. So we add this notation of plus 4.5, which means that in absolute counting, it's 7 pn. So they computed this and noticed that it's not systematic in the sense that, just to give you perspective, plus 4 pn is still incomplete. There is work ongoing on it, but it's still incomplete. Now, their credit should be given that while they were working, previous results from cell-force theory already existed that could be compared to some very partial results that they computed. I would say the simplest and the easiest, but obviously they tackle something which is much more extended than just what cell-force theory can give you in terms of what are the circular orbits around the Schwarzschild black hole, which is the type of things that cell-force theory provided. So to be fair, what are the pros and cons of these traditional GR methods? One challenge is that it is very laborious. From the time scale, you can see that it's quite slow. And the whole derivation builds on very specific definition, which is very much gauge dependent. On the other hand, it is a consistent approach that has been followed along the years, and it does provide solid results. One disadvantage, though, is that they handle separately the dissipative or conservative side. So that's why I wanted to highlight to you that, for example, in this recent result that they obtained, they tackled it as something that affects dissipation only. And this is a drawback in the sense that if you want to see some interplay of the effect between the two sectors, you better package it all together somehow. But really, the credit should be given that I'm pretty sure that this crowd is not aware of, that Luke along the years was, and still, the only one who provided actual amplitude and flux results to LIGO in a manner that billions and billions of dollars are basically based solely on computations that came from one group and are just barely starting to be confirmed now by EFT, but I mean, so again, respect should be given. Okay, so I started complaining about the drawbacks. And then there was this, what we call the first revolution of QFT toolbox to the rescue. And I want to highlight here two kind of seminal lines of work, which really correspond to this pictorial slide that I showed you in the beginning in terms of how to approach this type of effects. So the first paper was by Goldberg and Ross, 2009, and it tackled this problem by way of thinking of it exactly as what would be the 1-point function that one would measure from such a radiated graviton. So in general, this paper was very seminal. They formulated in general the EFT for radiative sector, really getting into the weeds of the more very general schematic description that was there in the original foundational paper of EFT. And the good thing about it is that, as usual in EFT, it provided clear separation of scales, and the whole standard Feynman toolbox is then opened. Included in it is the fact that we can borrow the background field method that we know usually from QFT, because we have a mixing of field modes from different scales, of momenta of different scales. But again, some drawbacks. So in fact, the background field method is also a drawback, as I will complain later. It also targets only, this work specifically was really targeting only the dissipative flux, but it did reproduce what was then the state of the art, which was the tail of the tail. And I would say that the significant milestone that really this work gave us, I mean, really revolutionary, I would say to an extent, is to show us that there is such a thing like a classical RG flow. And basically they demonstrated the leading classical RG flow of a quadruple moment as a consequence of them analyzing these types of scattering of radiation. So that was this very seminal work. But then there was a very nice guy who was operating more or less alone with the changing collaborators. His name was Chad Galley, and he again published his, I would say, first kind of more solid paper on this line on 2009, and stopped, left us sadly in 2017. And Chad brought in something very important to the table. He pointed out that, in fact, since the system is radiating, time reversal is broken. So we're dealing with an open system, and therefore we cannot just use usual QFT. We have to invoke what we call non-equilibrium QFT. And for that, we have what we call from non-equilibrium QFT, usually the closed time path formalism. And I will talk about it in a little bit. And once he did that, he also suggested this radiation reaction point of view that I showed in the beginning, which enabled to finally properly define the conservative and dissipative contributions of such effects. So there was a little bit of a trade-off in the sense that, as you could see from the pictures, it means that we're dealing with higher loops to compute, but then on the other hand, there are fewer graphs. It gives you more, so you can do less. And therefore, at least in the line of work that was forwarded by Chad, they only reached the tail level, and that's when they stopped. And there were afterwards, or also along the years, several follow-ups by Fulfan Sturani and some recent collaborators also, and a group that joined more recently from DESI. So I was starting to show you already signs of more complaint. And so the thing is that obviously I use the word scattering. What we have here is scattering of onshore radiation. So this suggests the fact that scattering would be more relevant to this situation than in other contexts. In IFT, for example, when we compute the two-body interactions, conservative interactions, purely conservative interactions, that's one thing, but also the fact that there is a mixing of field modes makes the derivation of final rules a headache, because eventually we have to integrate out all the field modes, and also the graphs become intractable. And in general, we have a headache, and kind of, as you could see historically, you see that it's kind of not progressing as fast as we would wish. So the mission that we set for ourselves, at least that I set for myself, was to see whether we can set something of an amplitudes-like framework, because I see that it could be something that can work quite naturally with an amplitudes-like framework to treat all these type of effects, which, as I said, could be any scattering. And I posed the following criteria on what I want from my framework to fulfill. I wanted to produce an output for an actual post-Newtonian binary in spirals, which is the kind of events that are measured by a LIGO and company and network. I want a framework that will capture the entirety of effects, namely both the conservative and dissipative sides. I want something that would be efficient and fast, to set up a framework conceptually, but also to set up the technology, the machinery that would be efficient and fast. And once I set it up, of course, I would be able, it would be natural to generalize it to all types of scattering in all PN orders. And just let me, again, highlight what I mean. Basically, there is some overlap from the two, and that means that I talk about scattering of radiation source from any type of multipole, and also going up in PN orders, even to subleading PN orders of the same nonlinearity in G would involve also changing source in multiples, which would mean different types of scattering in the sense that you will see here from the building blocks that we are using. And let me just mention that there is other work in amplitudes, quite recent and very fruitful, but which is tackling a different context and reach, scattering events, unbound orbits, post-Minkowskian regime. So there are quite a few groups already that approach this, let's say, family of effects. And forgive me if I forgot any group that already, because it's multiplying by the second. So forgive me if I forgot any group that already started delving in. So let's do like a quick intro on the closed time path formalism, just to tell you what we take from it for our thing. And in fact, as you will see, I mean, I mentioned it in the beginning, but eventually it will actually only come in the end in our framework. So essentially, time reversal is broken. We have a situation of an initial value problem instead of a boundary value problem. So we're dealing with an in formalism. A formalism was devised for that in the context of QFT many years ago, depending on if you ask Americans or Soviets, it's the physicists that you see here with the corresponding years. In general, in the context of QFT, we only have field degrees of freedom and they are all formally doubled, and the action becomes a copy of the action with one copy of the field degrees of freedom minus the conjugate of the action with a second copy of the degrees of freedom. But then this Chad Galley that I was talking about, it's a beautiful work, and he worked it out specifically because he wanted to adapt it to the problem of a binary in spiral, and he worked it out for the classical context by, I would say the important works that you will find is in this PRL, very nice PRL from 2012, and a very extended paper with some collaborators that really basically touches all options and cases that you can see here. And basically here you can see a cartoon of basically in this PRL, he formulated what would be the classical variational principle that would correspond to treating non-conservative systems. What does it mean practically in our case? Mind you, we are dealing with a classical wordline EFT. And so first of all, in general, that's not particular to us. It's very convenient to switch from what we call this first and second time branch or time history of the degree of freedom to what we call the plus minus basis, and they are defined as such. In our context, as I said, because we're dealing with a classical wordline EFT, we have these peculiar degrees of freedom which are discrete, so we will also double them. And also the classical propagator maxi matrix, which goes between these discrete degrees of freedom also, is completely off diagonal, which is true for the classical case. With the elements on the off diagonal, which are the retarded and advanced propagators defined just like that in a general D, which is spatial dimensions +1, with the plus E prescription to describe the retarded and correspondingly the advanced. Okay, so now let's approach our thing. What we want to do essentially is to use generalized unitarity to efficiently integrate out all the field modes that we need to integrate out. So we will start from the effective action of the composite binary, one which is very similar to a single compact object in the sense that you have a piece which is the bulk, and then you have the point particle effective action, and this is captured by an infinite set of multiples. Here I just show you the even parity contractions in this set of multiples because they are the only one that would matter for the present line of work. And we need to integrate out all the field modes in order to get eventually an effective theory, which will, it's no longer correct to call it effective field theory because there will be no field in it. It would just be a classical effective theory of discrete dynamical multiples that evolve in time. So what we will get information from this effective theory is basically on the evolution of these discrete degrees of freedom. So as I said, what we want to do is to integrate out the generalized unitarity instead of Feynman. And the generalized unitarity paradigm, where many people in the audience are the founding fathers of it, it tells us that we can basically account completely equivalently for the Feynman integration by essentially evaluating cuts, as I will show you. We can describe the effective action that we will get eventually as in an ansatz that will contain a set of master integrals that span the integrals that are relevant to the problem. And we'll have to fix the numerator of these master integrals. And in our case, notice that it's also a bit of a peculiar application in the sense that the frequency in our case, the K0, will actually act like the mass in what would be three-dimensional Euclidean momenta integrals. So therefore, that would be the form of our effective action, the effective action that we want to obtain. So let's see how it works in practice. So I will give more detail to radiation reaction detail, although they are quite trivial. But I think you pretty much get what is how it works. So essentially what one does is basically examine all the generic family of momenta invariants that are possible for the problem. In this case, it's trivial. There is only one loop. There's only one invariant, and therefore there is only one integral in the integral family that will capture all the problem, in general with some exponent lambda. But it's easy to see. Essentially, if you can also reduce it and see that essentially it can be reduced down to the same integral with an exponent of 1. And so this would be the general form that we expect for such an effective action. The cuts that we will use in order to evaluate these numerators that we want to target here, they will be assembled from three amplitudes that are extracted from the public code, increasing trees of Alex, my collaborator, and Fei Teng, my other past collaborator. And they will be glued with the graviton state swing, which is what you see here, that I'm pretty sure that most of the audience here is familiar with various tricks and ways to make this state swing more efficient, because I would say that this is the bottleneck of the process. And so we will do that. We know what is the state swing, and then we also need some expression for what would be these sources, some Lorentz equivalent expressions to handle these sources. And we make some actionable definition for this, which we can work with. And then we evaluate the cut in the usual way. We contract, we contract with the state swing. We put the cut propagator on shell, and this would be in general the expression for the coefficient. Now, if we then replace everything that went into these expressions, we would eventually find something that looks like that, where this kappa that I noted here will be a repeating creature that you will see here. So we will have a trace of the CTP quadruple degrees of freedom, because we will always have something emitting and receiving. And in this case, we will the layer of CTP that we will dress now the problem with would be to basically go over all the possibilities of such a trace that are possible within the CTP propagator matrix. So doing that and plugging in, comparing the coefficient, this would be what we would find for the effective action. And the thing is that also according to the trace that we take, according to the degrees of freedom that we take in the trace, this is how we will go over the possible I epsilon prescriptions in the propagator that run in this expression. And essentially that would be the notation corresponding to this propagator matrix that I showed you. And when we plug in everything, sum up everything, the expression that we get is that this is the effective action of the radiation reaction. I should just note that in general, every such effective action comes with zeros to infinity, essentially. It's zeros, simple zeros, double zero, and so on and so forth. And it's important to keep track of them because they will matter for higher order renormalization. When we later on, we will have pose. So I understand that I have to be very quick. Now I want to approach the tail. I have 3 loop momenta invariants. We plug it into your favorite reduction software. Fire is our favorite reduction software. And we see that it can be expanded by this with master integral with these 2 propagators in them. And again, we can write then the effective action in this ansatz form. And what we need in order to evaluate the corresponding cut would be an amplitude of 2 massive scalars and 2 gravitons, and it is extracted readily from increasing trees. And what we will do to it is only that we will expand it also in the large mass limit, because we're in the non-relativistic context, so all the rest will drop. And essentially, all the coupling constants, which are in general in amplitudes, are left kind of floating in the air, would be fixed by matching to leading vertices in the Feynman description. So by doing the regular sewing and evaluating the cut, we find some expression for the evaluation of the cut. We need to reduce it again to correspond to the master integrals that span the effective action, and we get this expression for the effective action of the tail. Again, you start to see here a pole, and I just want to ease you from worries and tell you that in general, these poles will cancel out from these zeros that exist in lower order effects. So I think that is the last slide of the methodology. So then I can really go really fast. So the point is that the derivation of physics is, if it's the conservative dynamics, is very straightforward. It's well known, and just have to follow basically the prescription, but we couldn't really find the proper derivation of dissipative observables from CTP effective actions. There were like various heuristic expressions hanging in the air for, but we couldn't find something rigorous derived, and therefore we ourselves worked out the generic derivation, starting a generalized Noether theorem that we apply for the quadrupoles as discrete degrees of freedom. Our CTP quadrupoles are CTP degrees of freedom. And all we have to do is identify in the expression that we have what is the conservative potential and what is the non-conservative potential. And that is, if we switch back to the 1 and 2 time branches of CTP, we will see that the conservative can be expressed as a difference of only the first time history and only the second time history, whereas the non-conservative potential will be entangling the 2. So as I said, CTP quadrupoles are generalized as the degrees of freedom. And what we would take from all that is that from this expression in time domain, we would eventually derive the power spectra in the frequency domain. So this is just to flesh out from this point onward, is just the results that we got. So essentially we went up and implemented the same approach to the next order effect, the tail of tail, and we got effective actions that were never derived, really following the same procedure that I described. Similarly for tail of tail of tail, in fact here the effective action was so lengthy that I couldn't even put it on the slide. And just using this generalized Noether theorem that I showed you, we were able to derive all the power spectra. In particular, we found recent work from Bini and Geralico that actually half of the paper was about getting this power spectra by Fourier transforming from known expressions in time domain. But the TTT power spectra is, to the best of our knowledge, completely new. And from this general power spectra, we specified 2 circular orbits, which means that we specified some circular orbital frequency and some microphysics of the quadrupole. And we got complete perfect agreement of our results with traditional zero force and post-Newtonian theory results. So this is the summary of what we obtained. We obtained effective actions that encapsulate all conservative and dissipative physics, including tail of tail and tail of tail of tail that were never previously derived. It was proven that by checking dissipative observables, it all matches with results where they were available. We set an amplitudes-like framework and machinery for hereditary effects directly applicable to PN binary in spirals. It's proven to for-loop order. It's efficient and fast. And it's, as I shown, we reached the state of the art and beyond what we could find in traditional GR, and clearly surpass what standard EFT has achieved so far. And it's very clear what are the two avenues to go along with the ones that I noted in the beginning. It's either to explore any scattering from any multiple source of any other multiple source background. And it overlaps also with extending these corrections essentially to any PN order. And both of these two things actually are also interesting from the amplitudes perspective, because both of them would require to have readily 3 amplitudes with massive particles of any spin. So with that, I finish and I thank you very much.
Thank you, Michelle. We have Julio.
Hi, Michelle. Thanks for a nice talk. This is Julio. So if you try to do this because you're matching an off-shell effective action. So if we try to do this in quantum field theory, there's an issue if you cut legs, which is that it's hard to align the field bases at different orders. So if I do a field redefinition, I would introduce pinches that are not captured by the cuts off-shell, because you're putting all the sources on-shell. So is this problem not in your setup because you're computing the tail contribution, so that pinch will be some scaleless integral? And if that is the case, wouldn't it be a problem if you put generic multiple sources?
I mean, in general, your question is, I mean, there are 2 parts to the question. Some part of it is a conjecture of what will happen beyond this, what is the simplest prototype of this type of effects. Obviously, the tails are the simplest. So I don't know what is the answer. We'll just have to try to keep pushing. But I think that to answer, I think what was the first part of your, I'm not sure I completely understand what you're asking, but I think that some of the secret lies in the order of operations, because essentially we are completely agnostic to anything about the CTP prescription, the integration. We really postpone it to the very end. So basically, up to the stage that we get some expression from the evaluation of the cut, the evaluation of the cuts proceeds exactly as if it would proceed in your world. So.
Right, but you're matching an off-shell action, right? So this will give a unique answer, but we know that the answer is not unique, right? Because we can do field redefinitions. So that's my confusion, basically.
But what makes it off-shell is like once why do you say that I am? It's only after integration that it's only after I move into this 3D world that it becomes a 3D object. But before.
So I think it's off-shell because the multiples are just generic objects. They're just like field variables. You don't plug in like a solution of the equation of motion or what the multiples would be, right? This is completely generic.
Yes.
But maybe we can discuss offline. Thanks.
Yeah. Okay.
Yes, Zvi has another question.
Hi, Michelle. This is Zvi. Thanks for a very nice talk. So right up on the slide there, it says directly applicable to the binary and spiral. Might you have some insight on the analytic continuation from the unbound case to the bound? So in scattering amplitude, generally we have, of course, the unbound case. And you'd like to directly do the translation. Anyway, do you have any comments on that or thoughts?
Following many inquiries by colleagues on this issue, I've honestly come to the conclusion that what exists so far is some sporadic observation about, I mean, sporadic in the sense that it exists only for some case, only in a restricted configuration, which is the connection between a scattering angle and the angle of periastronal bands, which is what and then like this like magical ansatz that worked in the nice work of the Potsdam group. I mean, it worked for the sector that they implemented it, which there is some kind of universal form of a Hamiltonian that would hold equally well for the bound and unbound case. And that was like an assumption, a working assumption, you could say. I mean, it's not proven, but it worked. So, I mean, it's interesting. But that's all I could collect, and I was struggling to collect, you know, what is the current status of actual connections. But okay. I mean, I'm also saying this directly applicable in the sense that that I'm trying to bypass as much as I can roundabouts, you know, like the roundabouts of like struggling with getting it in this context and then moving it to that context. So it could be obviously that, and also definitely intellectually, it's very worthwhile exploring what are the connections between these two worlds. So anyway, I mean, we should explore the other world of the scattering and see how it connects to the unbound to the bound. But in terms of direct applicability, I mean, that was my kind of driving goal. And I'm actually myself very curious about the question that Julio asked, because I mean, my wishes came true. That's exactly all I wanted from the project happened. So, you know, it's too good to be true. So I always like, oh, maybe we got lucky because it's only tails, or I don't know what, but we will have to just keep exploring.
Maybe we have one quick question and a quick answer before lunch from Dimitris.
This is Dimitris. Thank you for the very nice talk. I had a question about the diagrams in this formalism. For example, on slide 10 or something around there.
Oh, what's
the double line that depicts the matter. My understanding from reading the paper is that you don't use propagators for the matter line. How come there is no matter propagator for the double line, the off-cell double line inside these diagrams?
Yeah, I mean, you can think about it as like you would pinch this. You can pinch this. You can take this graviton and attach it. You can take this three vertex and attach it to the word line. And there, I mean, you only have to keep track of the propagating degrees of freedom, which we consider not the word line. And therefore, this is why this captures correctly all the information in this Feynman integration.
So the word line doesn't propagate off cell, the matter doesn't propagate?
No, doesn't. No, not in our description. I mean, we are truly using generalized unitarity to integrate out our degrees of freedom, which are considerably simpler than I think all the formulations that the people in the audience here are using. And that's part of the thing. I'm going for less baggage, for easing the extra baggage. So so yeah, I mean, but do you basically, do you see what I mean? You just like should basically only follow the gravitons in the, and then you can just
yeah.
And then if you pinch this potential graviton, if you will degenerate it, or I don't know how to say it, collapse it. If you collapse it, then that would be the cut that you're seeing.
Yeah, thank you.
Okay, thanks, Michelle. Let's thank Michelle and all the speakers of the session.
Thank you.
So please come in, everyone who is close to the door. All right, welcome everybody to the last session of this lovely conference. In view of constraints from the coffee break thereafter, I was told to have 2 eyes rather than 1 eye on the schedule. Having said that, it's my pleasure to welcome the first speaker of this session, Callum Jones from UCLA. Please take it away.
Hello. Okay, thank you, Oliver. And let me start by thanking the organizers for all their hard work in putting together this wonderful conference and for inviting me to give a talk. And thank you to all of you for sticking around until the final session. Hopefully you're all still alive. So this talk is going to be in line of the talks from today and yesterday on classical gravity, but hopefully in a new, exciting, orthogonal direction. So I'm going to tell you about some work that appeared on the archive last week in collaboration with Mikhail Solon at UCLA on the n-body problem for classical gravitational physics from scattering amplitudes. So why should we care about n-body physics? So n here is some number bigger than 2, and the reason is essentially that these systems, though they may be rarer than binary systems, are by no means impossible in nature. There are many, many interesting astrophysical examples that appear on a wide variety of scales. So all the way from our nearest stellar neighbor, the Alpha Centauri system, is a hierarchical triple star system, all the way up to this image, which I took from this paper, which was created by some astronomers working with images from the Chandra X-ray Observatory. And it depicts a triple system of active galactic nuclei, which means that it's a triple system of supermassive black holes that have formed a bound state following a triple galactic merger. The other reason is not just because these are common systems or not uncommon systems in nature, but because they have incredibly rich physics. So again, this is a plot that I stole from this paper. And it's a very, very interesting first of its kind numerical relativity simulation of a triple black hole system undergoing sequential merger. So that means that there are 3 black holes, 2 of which merge at some early time, and then the third one merges sometime after that. And the resulting gravitational radiation that has this extremely interesting sort of double in spiral ring down pattern. So the question that I'm going to try and address in this talk today is to ask if, given this incredible success that we've heard about from Zvi and others today about calculating post-Minkowskian and post-Newtonian effective theories for gravity, is some part of this physics, maybe the early part where these bodies are well separated, captured by some sort of post-Newtonian expansion, and can we calculate that from scattering amplitudes? From a theoretical point of view, this question is interesting because it illustrates a big conceptual difference between Newtonian gravity and Einsteinian gravity. So in Newtonian gravity, the force law, or the equations of motion, for an n-body system are trivially different from the 2-body system. If you know Newton's law between 2 bodies, then Newton's law for n bodies is just given by summing over pairwise interactions of 2-body potentials. So in other words, more is the same for the Newtonian n-body problem. This is just at the level of the equations of motion. Of course, the solutions to those equations are famously chaotic and extremely complicated and so on, but at this level, it's sort of trivially different. Einsteinian gravity is very different from this. It's an intrinsically nonlinear theory, which in the context of these kind of effective potential systems means that knowing the 2-body dynamics is not enough to know the n-body dynamics. So even if Zvi and friends compute the 2-body post-Minkowskian potential to 20 loops, as soon as you throw a 3rd body into the system, you have no idea how that system is going to evolve because there are intrinsic 3-body, 4-body, 5-body, etc. forces that are new and need to be calculated through some different calculation, some different matching calculation. So the first example, the earliest example of an intrinsic n-body force was calculated long ago by Einstein and Veld and Hoffman and takes some form that looks like this, depends on the coordinates of 3 of the bodies at the same time. So the basic question that I'm going to try and address in this talk is what is the gravitational potential between n compact bodies? And naturally the way we're going to address this question is with scattering amplitudes. So to give some sort of overview, what is this talk about? I'm going to present a general framework for calculating n-body potentials for n greater than 2 using scattering amplitudes methods. Since it's a very limited time, I'm going to focus primarily on what parts of this calculation are new for n-body versus 2-body. So what are the new and interesting challenges that emerge at higher multiplicity? In terms of explicit results, I'll present an explicit calculation of the order g squared, or 2pm three-body potential in general relativity, and also in Einstein-Maxwell theory, so for charged compact bodies. And I'll explain later on why we did this calculation. It's sort of marginally more difficult, but physically very rich. And then in the final part of the talk, I'll present some robust evidence, a series of checks to show that our calculation was correct and it's calculating the thing that we think it is. What this talk is not about, unfortunately, it's not about solving the n-body equations of motion. Interesting questions about numerical methods, finding exact solutions, post-Newtonian corrections to chaos. And it's not about the astrophysics of n-body systems, dense star clusters, hierarchical systems, or gravitational waveforms. These are all extremely interesting and very important questions to answer, but today the focus will be on determining the equations of motion. Okay, so even without knowing sort of in detail how these calculations are done, there's some sort of rough correspondence between Feynman diagrams and potentials. And the reason we get intrinsic 3- and 4-body pieces in the potential from this point of view is because there exist Feynman diagrams like this, where sort of 3 or more gravitons sort of meet in the middle of a diagram. And this can't be separated into just pairwise interactions. So you can determine the leading order contribution to the intrinsic n-body potential by looking at the lowest order tree graph that you can draw that's completely connected and counting the number of powers of g Newton. So for example, for this the leading 3-body interaction comes from some diagram that looks like this, that has 4 vertices, and so it gives an order g squared contribution. The leading 4-body force has 6 vertices, so it's a g cubed, and so on. So before I tell you, sorry, that's what I just said, that you need finite multiplicity to calculate an n-body potential, even if n is some number larger than this. So before I tell you how these calculations go and what the new results are, let me try and summarize for you the state of the art in this problem, since I take it most of you have probably never thought about this before. So the original calculation of this kind was done by Newton. Not really a calculation, but wrote down the n-body gravitational force law as soon as he had written down the 2-body gravitational force law. In the language of Feynman diagrams, this contribution corresponds to a 2-body tree-level contribution. The first post-Newtonian correction, which I said before was computed by Einstein, and Hoffman, has 2 contributions. The first is a 1-loop 2-body piece and a tree-level 3-body piece. And then the pattern continues. So in terms of calculations that have actually been completed, the state of the art is second post-Newtonian, where there's a 2-body 2-loop contribution, a 3-body 1-loop contribution, and a tree-level 4-body contribution. These 2 things were calculated in a series of papers that ended in 1987 with a nice calculation by Gerhard Schaefer, who wrote down the explicit answer. And actually, that's the end of explicit new results in this subject. So the state of the art has not moved since this date. So the 3-body 2pn potential is completely known, but for general n bodies, say if you wanted to do a 10-body n-body simulation, you would also need this piece, and this is not known. And I'll explain when we get to it exactly why that is and which part of it is not known. So in light of this sort of not particularly impressive status of the subject, the question we want to know is, can scattering amplitudes methods help us to push the state of the art for n-bodies in general relativity? Okay, so we've sort of heard many talks on this today, but let me just sort of in very, very basic terms review how we determine a potential from a Feynman diagram calculation or from a scattering amplitudes calculation. And the idea is that you basically calculate the same quantity in 2 different formalisms and require that they give the same answer. So the first is you compute Feynman amplitudes using sort of manifestly relativistic scattering amplitude, the normal quantum field theory type scattering amplitude calculation. And then you compute the same quantity, a scattering amplitude, but in potential scattering theory, the kind you might learn in a graduate quantum mechanics class, for example, by solving the Lippmann-Schwinger equation for some potential. So this is something that you know and you can calculate very well. Everyone in this room is aware that calculating high multiplicity and high loop gravitational scattering amplitudes is feasible now more than ever because of all sorts of on-shell magic, like double copy, generalized unitarity, etc. And so we require that these 2 things give the same answer in a particular limit, which is the limit of small 3 momentum transfer between the bodies. Roughly this corresponds to sort of integrating out potential mode gravitons and generating some instantaneous potential. So the primary example that I'll use to sort of illustrate this framework throughout this talk, and that we'll end with the explicit calculation, is the calculation of the three-body potential at order g squared. So this is a tree-level calculation on the field theory side. So roughly speaking, you have some of a Feynman diagram, some of which look like this, some of which look like this, and this should be equal to some contribution from potential scattering, where these are supposed to be terms in the Born series solution of the Lippmann-Schwinger equation. So there's a leading order firstborn approximation term, and then there's an iteration of lower order terms. In equations, this is exactly what you learn in your graduate quantum mechanics class. The only difference is that the energies that we use in this formula are the full relativistic energies. So what we care about actually is this piece, the sort of contact piece of the potential, and not this piece, which is an iteration of lower order things that you're supposed to have already calculated. And so you just rearrange this formula and move this thing to the other side, and you get some schematic formula that gives the potential in terms of Feynman diagrams minus iteration pieces. And then finally, you take the appropriate limit at the end. You take the h bar goes to 0 limit, which more technically means you expand in this small momentum transfer up to some order that you can compute by dimensional analysis. And in this particular multiplicity for this order, turns out classical order is 1 over q to the 4. Okay, so the slogan for this part of the talk is going to be that more is different. I want to tell you the various ways in which this calculation, which superficially looks very similar to the two-body calculation, is different, and the sort of methods for overcoming these difficulties, outstanding problems, etc. Okay, so the basic structure of the three-body potential that you calculate looks like this. There's kinetic terms, there's some two-body pieces and some three-body pieces, which in momentum space, importantly, these pieces have different delta function support. Roughly speaking, this thing has dependence only on the positions of bodies I and j, and so when you do a Fourier transform, you get more delta functions. And the consequence of that is when you compute this iteration piece, this second-order Born series piece, you're instructed to do some phase space integral over these intermediate particles, and these delta functions on the two-body interactions completely localize these things. And so you end up with something new that doesn't show up for the two-body problem at all, which are these EFT or iteration type graphs which have a tree topology. So in the two-body problem, the EFT iterations just look like bubbles after bubbles after bubbles. So one thing you realize when you stare at this for a few seconds is that one of the standard assumptions that people make in the two-body calculations isn't going to fly anymore, and that is that you can't just make the assumption that you're calculating the two-body potential in the center of mass frame. So even if the momentum coming in on this leg, P1 and P2 are equal and opposite, they're not going to be equal and opposite by the time you get to the second vertex, and so your input needs to be the calculation of a potential in a general reference frame. And more generally, the k-body potential for k less than or equal to n in some general reference frame is needed as input for the n-body calculation. So these are done sort of sequentially in the number of external states. So before I can continue, I need to make a small digression on a technical point to address something that confused me a lot when I first started learning this subject, which is to address the question of why is the effective potential not gauge invariant? So from a basic GR point of view, that's an obvious point. The potential is some function on position space. In general relativity, we have coordinate diffeomorphisms that should mess up the potential in complicated ways. Clearly not a gauge invariant observable. What's confusing is that in this subject, you compute the potential by matching to a scattering amplitude, and you get some equation like this, where on the left-hand side you have a gauge invariant scattering amplitude, on the right-hand side you have a gauge dependent potential. So how can this equation possibly be true? The resolution is that this matching equation, this Lippmann-Schwinger equation, is only true or only holds on a particular constraint surface that enforces energy conservation for the bodies. So in three-momentum language expanded to classical order, energy conservation for two bodies is some combination of things like this that has to equal 0. And the potential is defined by matching these things on this surface, but then continuing it away from the surface. So whenever you have this sort of situation, there's always an intrinsic ambiguity. And so you can take any solution to this equation and you can just add something like this, some function that vanishes on this constraint surface, and you get a different potential. And this is a huge gauge ambiguity in what you mean by the physical potential, and it sort of encompasses these coordinate transformations in position space. So what am I supposed to do about this? Well, in the two-body problem, there's a sort of canonical way to deal with this ambiguity, which is that you use this freedom to rewrite dot products, p dot q type dot products in the following form, where all the dot products are written as p1 plus p2 dot qj. And then if you make the standard choice that people do, that you're working in the center of mass frame where p1 plus p2 is 0, then this is 0, and that lets you get rid of all of the dot products, p dot q. And this enormously simplifies the potential. It makes the calculation a lot easier. It also underlies things like boundary to bound and other ideas. And it's a hugely profitable thing to do, but it's not going to work for us because we're not able to choose the center of mass frame. The best we can do is to use this freedom, as I said, to rewrite all your dot products as p1 plus p2 dot q. And so if you do that, what it does for the two-body at 1 p.m. Potential is it gives you some answer that looks like this. So this is the generalization of isotropic gauge, generalized isotropic gauge answer. And the primary difference is that the graviton pole gets displaced after you resum all of the velocity corrections. And so you end up with these so-called energy transfer pieces. If you care to know, after you put this thing into position space, this is what the general reference frame two-body potential looks like. It's sort of considerably more complicated than the usual center of mass frame expression. Okay, there are similar ambiguities, exactly similar ambiguities that show up for the calculation of the three-body potential. Here's the matching equation sort of schematically. Again, you can simply take any solution to this matching equation and then change the answer by adding something that vanishes on three-body energy conservation. And the difficulty here is that there is no canonical choice for how to deal with this ambiguity. There's nothing like generalized isotropic gauge. And so we just have to live with the fact that different people computing the same quantity are going to get different answers. So how do we compare potentials that are computed in different gauges? Well, there's essentially two choices. One is that you can calculate explicit canonical transformations between them. And then the other is that instead of doing that, you can compute physical observables and compare those. And the second option turns out to be much, much simpler in this context. These canonical transformations are extremely complicated because of the number of variables. So the physical observables we're going to calculate to compare today are going to be the classical scattering amplitudes themselves. From a technical point of view, that's a physical observable because it's gauge invariant. But if you don't like that because you'd like to know what an actual observable is, as David explained to us today, you can think of the classical S matrix or the classical scattering amplitude as being some proxy for any observable that you can put into the KMOC, for anything you can put into the KMOC formalism and get out some classical observable for unbound scattering. So for example, an impulse or an angular impulse or something. If you agree on the S matrix, the classical S matrix, you have to agree on these observables. Okay, so let's go back to these iteration graphs with the tree-like topology. So they have a clear problem, which is that they naively contribute to the potential in a form which has a singularity along this matter propagator. But that singularity shouldn't be there. The propagator, the potential is only supposed to have singularities where you've integrated out some state to build your effective theory, and this matter line hasn't been integrated out. So you shouldn't have a singularity in your potential. You might have thought that there's a corresponding graph in the full theory that when you subtract, which has the same matter singularity, so that when you subtract the two, you just get nothing. But a careful analysis shows that this expectation is actually incorrect because of this subtlety with these energy transfer pieces. The energy that is transferred in full theory graphs and in EFT graphs is actually subtly displaced from one another. And so there's no possibility that you could subtract these two functions and get 0 because they literally have different singularities. And it's interesting that you don't see this if you do an expansion to any finite order in post-Newtonian, because these energy transfer pieces are always subleading. It's only after you do the velocity resummation that you see these two functions literally just have singularities in different places. So what you have to do is you have to be clever and spend that gauge ambiguity that I just told you about in such a way that you can rewrite this difference in such a way that this spurious singularity cancels, and you get some residual thing left over that has only physical singularities. So in general, there's a sort of art more than science that we explain in detail in the paper for how to spend this freedom. And we propose that there are sort of a set of physical acceptability conditions that you should satisfy. The first is the cancellation of these spurious matter singularities. The second is the cancellation of superclassical terms. So I didn't say this yet, but these graphs are actually individually scaled like 1 over q to the 5 in the small q limit. So they're superclassical, or 1 over h bar. So these have to cancel when you sum graphs with their crossed graphs. And then finally, you want to maintain the sort of manifest permutation symmetry among the external states. Okay, so the final new thing that is potentially the most severe bottleneck for calculating these n-body Hamiltonians is transforming them into useful position space expressions. So what I've told you so far is how to calculate momentum space Hamiltonians, or momentum space potentials, but that's not what you want to hand to an astrophysicist to do an n-body simulation. They actually have to solve Hamilton's equations in time and so on. And so you need to give them some position space Hamiltonian. The post-Minkowskian version of the integrals you need to compute are completely intractable as far as I can tell. So let's be less ambitious and see if we can do these Fourier transforms order by order in velocity. So for this problem at this order that I'm considering, the kind of Fourier transforms you need to compute look like this. They correspond to graphs like this. They have 3 graviton poles and some 3 momentum conserving delta function, which if you transform, if you do some standard manipulations, these turn into an ordinary-ish looking Feynman integral computed in 3 dimensions with a sort of triangle topology, but with the obnoxious feature that these things are raised to these propagators are raised to half integer powers. And the problem in this subject is that most of these integrals are not known. So at 1 loop, so this would be g cubed, 3 bodies at g cubed, you would get some Feynman integral like this, where you have an ordinary propagator and 2 square root propagators. And at 4 body at tree level, so at g cubed, you get what is equivalent to a 2-loop Feynman integral, again with square root propagators. And I said before that the 4 body at 2pn contribution had never been calculated in closed form. And the answer is that, the explanation for that is that it's known up to the evaluation of this integral, but it's never been computed in closed form. And so there's no closed form expression for that piece of the potential. Okay, in light of time, I might actually skip through some of these things, but I'll just highlight that there's an interesting, outstanding problem to calculate these 3-body Fourier transform integrals. So for 3 bodies, what you need is generally to evaluate this thing for general exponents alpha 1, alpha 2, alpha 3. At the order that I'm interested in, these have actually all been calculated. There was a nice guess in this paper that the space of functions only involved these logarithms. Turns out that had actually been calculated before by some people working on a completely unrelated problem of computing the momentum space 3-point function in conformal field theory, where they showed that these things can be reduced down to some single Schwinger parameter integral over a product of 3 Bessel K functions. And you get a very simple space of functions for this because the indices on these Bessel functions turn out to give you elementary functions for this special case. Okay. I'm going to skip through this, but as I said, there's an interesting outstanding problem for how to calculate these integrals. Okay, so let me tell you about our explicit results. So the calculation that we did was to calculate the 3-body potential in Einstein-Maxwell theory. So in these diagrams, these wiggly lines are either gravitons or photons. I'm not drawing all the diagrams. So the answer has essentially 4 different pieces. The first pieces correspond straightforwardly to these Feynman diagrams. They call them the Y-type piece and the V-type piece. And there's no trick and no subtlety in computing them. They're literally just the negative of these things expanded to classical order. So there's what it looks like. There's a piece that corresponds to these Feynman diagrams which have a matter propagator, which in this subject it's useful actually to separate that into a positive and a negative energy solution and then interpret it as you would in time-ordered perturbation theory. So there's a piece that corresponds in time-ordered perturbation theory to this process where you have particle annihilation and creation, which is a very quantum mechanical process. And so unsurprisingly, when you take the classical limit of this thing, well, you don't get 0 as you may have thought, but you get something that has no matter singularity. So you get a contact contribution. And then there's a final piece, which are these subtle subtraction pieces I told you about, which do have physical singularities in the classical region. But there are some manipulations that you can do to put this in a form where the spurious singularity is canceled. And this is what the answer looks like. So everything that is in blue here is something that depends on the actual physics of the problem that you're interested in. So the fact that we were computing in Einstein-Maxwell theory. Everything else is universal or theory independent. So if you were to do this problem again with spin or massless scalars or Yang-Mills or whatever, you would get the same structures. These expressions have manifest. It's manifest that there's no spurious matter singularities anymore, but it's not manifestly classical. The these superclassical terms cancel due to some symmetry properties that are engineered into these numerator functions. Okay, so this answer is kind of complicated, but this is actually just what nature looks like. This is the three-body potential in our universe between massive bodies at order g squared and all orders in velocity. So in the few minutes that I have left, I want to explain to you why we know that this calculation is correct. So the first series of checks that we did was to compare with these known post-Newtonian results. So the state-of-the-art calculation that we could compare against is at order g squared, which was from this paper by this group of people. So they computed a formal post-Minkowskian result using world-line methods. But if you want to turn that into an ordinary Hamiltonian, you need to do a series of complicated field redefinitions to remove higher time derivatives. And they did that explicitly up to g squared v to the 4. This is the g squared v squared answer. At this order, the answer has sort of 5,000 or so terms. But we took their answer and we computed a classical scattering amplitude from it, and we found perfect agreement. So the second series of checks, which I'll go through quickly, were about, so one unfortunate feature about this comparison is that we had to do a velocity expansion. So we lose information that is all orders in velocity, and therefore some of the benefits of doing a post-Minkowskian calculation. So you might wonder if there is some calculation you can do where you keep all orders in velocity, perhaps a probe or test mass limit. So you can do the most obvious test mass type calculation where you have one background and two probes. Unfortunately, this is trivial from the point of view of three-body dynamics because by definition, these two probes don't talk to each other, so the Hamiltonian splits into a sum of two terms. So what we need are multi-center black hole solutions, and this is why we did the calculation in Einstein-Maxwell. So in Einstein-Maxwell, you have access to these Majumdar-Papapetrou solutions, these multi-extremal black hole solutions, and you can do a different kind of probe calculation where you put a charged relativistic probe on this background, and now you can compute a probe Hamiltonian up to the order g squared, and then you'll find that you get some Hamiltonian which does have three-body interactions. You can compute three-body scattering amplitudes from these things, and you again find complete agreement to all orders in velocity. There was a final check that we did, which I'll just say very quickly, involved three black holes in the so-called moduli space approximation, which means that it was computed to all orders in g Newton, but leading order in velocity squared. And again, if you expand out and collect to the relevant order, you find exact agreement with our result. Okay, so I'm out of time, so I'll just say, I hope I've convinced you that n-body dynamics are an exciting new direction for gravitational calculations in scattering amplitudes methods. But thank you very much for listening. Sorry, Oliver, for going there.
Yeah, thank you so much, Callum, for this enjoyable journey into n-body land. Are there any questions to Callum?
Hi, thanks a lot for the talk. I was just curious if there's any notion of iconal for three or more bodies.
That's an excellent question. As far as I know, the answer is no. But this would be extremely interesting to think about. Yeah, I don't know if anyone here has an answer to this question, but come find me afterwards.
Thanks.
That's V, please.
You did an enormous number of checks, some of them very complicated. What was the reason you were worried, beyond the, let's say, the first couple checks you did?
Well, I guess it was just good practice. We wanted to make sure that we agreed with every result in the literature that we could find. And we also wanted to set up something that, in principle, we could do. If we do the next order and the next order, we'll also be able to do those checks, where it may be less trivial. So I sort of went through it very quickly, but one of the reasons why this check is so interesting, sorry, this one, is because this prediction is all orders in g Newton. So it doesn't matter how high in loop order you go, you always have some piece of the answer that is completely, the leading order and velocity piece is always completely fixed. And then there's a sort of, you can turn it on its head and you could say, we're very confident in our methods. Like we did the calculation correctly, but this whole program, this moduli space calculation, is based on a sort of conjecture that Manton made a long time ago. And so the fact that we agree could be viewed as a check of their result. If you know, depends what your Bayesian prior of confidence is, but.
We could do another very short question. Julio?
Just very quickly, this is only up to order v squared, this sort of computation. Does your result suggest how to go beyond in this sort of moduli space approximation, or can you glean something from there that you could use to, because I think people haven't gone beyond the first order in velocity in this business, right?
Sorry, I didn't hear the last part of what you said.
That people didn't go beyond v squared in all of these moduli space problems, right? But
right.
there might be some systematic expansion.
As far as I can tell, there's no reason why this, I mean, eventually radiation will become an issue, but at low enough orders, I think, so v to the 4, I think maybe you might still be okay. I don't see why you couldn't systematically do it. I mean, you're supposed to think about this thing as a sigma model Lagrangian. So why, where this complicated function is some metric. So, I mean, you sort of parameterize the most general sigma model Lagrangian with 4 derivatives instead, and now you have a bunch of coefficients you need to calculate, and maybe you can match those from our answer. That seems like a reasonable guess, but as far as I know, there's no actual data. No one's actually done the v to the 4 version of this calculation.
Mm-hmm. Okay, then it's time for another big applause for Callum. Yeah, then I'm looking forward to hear our next speaker, Gustav Mogul from Humboldt University Berlin and from Albert Einstein Institute Potsdam. Please go ahead, Gustav.
Thanks, and let me also extend my thanks to the organizers for giving me the chance to talk at this wonderful conference. So I'm going to be telling you today about this series of ongoing work which I've been doing together with various different subsets of these people based at Humboldt University and the Max Planck Institute in Potsdam, Jan Plewke, Jan Steinhoff, Gustav Jakobsen, and Benjamin Sauer. And what we've been working on is what we call the world-line quantum field theory, which is a technology that we're now very fond of and which we've been developing in order to help us tackle scattering problems in the gravitational two-body problem, like many people here. And in particular, we've been looking at how we can tackle scattering involving spinning black holes and indeed neutron stars, which involves a supersymmetric extension to the world-line theory, hence the name of my talk, Susie in the Sky with Gravitons. So in order to begin by setting the stage for this, let me just for the time being focus on the non-spinning problem, just to keep things simple. Now, unlike many of the talks that we've heard here today, where one often thinks about, for example, a scalar field theory being used to describe a black hole, we've taken a different approach. What we do is we focus on What we focus on is a pair of world-line actions, which we use to describe our two black holes. So we couple this to our Einstein-Hilbert term describing our gravitons, and we have a pair of world lines for our two black holes. And this is exactly the same starting point as one uses in the so-called world-line EFT approaches, which have been pursued in the post-Minkowskian context by, for example, Gregor Kell and Rafael Porto and collaborators, and also various other groups. And the idea here is that we have our trajectories of our black holes, which we expand around some straight line trajectory. We have some deflection, z, and then we, of course, have our gravitational field. And the idea is that we promote both the deflection modes and the graviton to be propagating degrees of freedom in this theory. And that's the key distinction with the EFT. In the EFT, you only promote the graviton, and you leave the deflection mode alone. So you first integrate out the graviton to build an effective theory, and then you solve equations of motion. The reason we do it this way is mostly practical. We find it's simpler. We have a one-step process to calculating observables. But from a philosophical standpoint, what we really want to do is we want to take what you might call the amplitudes philosophy and bring it to the world line. The idea there being, of course, one shouldn't think about off-shell quantities, at least as much as you can. You should try to focus always on physical observables. So that's what we do. We're always focusing on physical observables. So what we build up then is a theory where we have propagation of both the gravitons and these deflection modes, but the deflection modes propagate only on the world line. And the world line is one-dimensional. So when you look at these vertices, which now exist on the world line is represented by the dotted line. For example, we have here a source of h mu nu, and you have a vertex here which conserves a one-dimensional component, so that would be an energy component. And you can just read that off from the action. Similarly, you can have vertices which mix up the gravitons and these deflection modes, z. And why do we think that this is a convenient way to work? Well, it's because what we've heard from a lot of people so far is that one should not make the mistake of assuming that the loop expansion is the same as the h-bar expansion, because it's not. But in this case, it is. In the WQFT, when we start from the world line perspective, it is the loop expansion. You can very quickly convince yourself that tree level is going to correspond to solving the classical equations of motion. Well, I mean, this is just a known fact, but the point is that in this case, the equations of motion of this theory are just going to be the geodesic equation and the Einstein equation, which is exactly what it is that we're looking to solve. So what we're going to do here is we're going to focus on tree level, but we're going to see how, nevertheless, we start getting loop integrals appearing in this framework. But now the question is how we start incorporating spin. So the way that we build spin into this framework is we take a supersymmetric extension of the world line action. So what we introduce is these Grassmann-Odd psi vectors, which encode the spin degrees of freedom on the world line. And this particular action, which I'm using here, is valid up to quadratic order in spin. So in Amplitude's parlance, that would be spin 1, or in other words, quadrupoles. So we can think about our spin tensor, S mu nu. We can build that up by forming an outer product between these spin vectors, which are, of course, anti-commuting. And you can quickly convince yourself that this is a sensible definition of spin just by looking at the algebra of this theory. So if you take your Poisson brackets here between psi and psi bar, if you then just take this definition of the spin tensor, you'll then see very quickly that it satisfies the usual spin algebra that we would want. And indeed, that's how you fix this minus 2i normalization that I have there. Of course, in order to show that this truly describes the correct physics, you need to look at the equations of motion and show that they're the correct equations of motion for the theory, but that we have, of course, done. What's really interesting, though, of course, is the supersymmetry. So what actually is this supersymmetry? What is this doing? Well, in order to help explain it, let me just focus on the case of flat space. What the supersymmetry really represents is a very basic fact about spinning bodies, which is the fact that there is no unique definition of the spin tensor. It depends how you pick the center of mass of the body. So what you can do is you can shift terms between the orbital and spin components of the angular momentum while leaving j mu nu invariant. And the reason it's a supersymmetry is simply because you're representing it in terms of these Grassmann-Odd variables. So in order to fix this symmetry, what one typically does is imposes a spin supplementary condition. And the one that we find most convenient to use is the so-called covariant spin supplementary condition. And unlike the world line approaches which we saw earlier, where one often needs to introduce a Lagrange multiplier in order to enforce the SSC, we don't. The enforcement of the SSC for us is guaranteed by the fact that we have this supersymmetry. P dot psi is in fact a conserved charge of this theory. So it allows us to keep things much more minimalistic, which is great for when we want to describe propagation in this theory. So the first example of something that we looked at, which involves this theory, the first thing we calculated was the spinning waveform. So the waveform produced at leading order in G, so that's 2 p.m., from a scattering of two spinning black holes up to quadratic order in spin. And as I say, the way we do that is we draw tree-level diagrams, and in this case, we're looking for the diagrams with a single outgoing graviton line. So we can have deflection modes propagating on the world line, and we can also have spin modes propagating on the world line. Now, in the amplitudes context, the equivalent calculation that you would do is you would look at a 5-point amplitude. But the difference is that if you were looking at the 5-point amplitude, you would then have to take the classical limit of this thing to get the waveform. We don't have to take the classical limit. For us, we simply write down the sum of diagrams, and once we've done the relevant integrals, that's it. We have the waveform. There is one additional step, though, in order to get the time domain waveform, which is we need to integrate on the energy of our outgoing graviton line. So essentially what we do is we just point the graviton towards the observer using this n vector, and then we have omega, which is the energy of the graviton. So we just fire it towards the observer, and we integrate on the energy. And so in this paper, we did indeed build up that waveform, and it's a fairly complicated expression, but there it is. So But what we've now been working on more recently is we've been looking at free PM observables, and we've been building up scattering observables. And like many other people here, we're interested in the impulse, delta P, and the spin kick. So for us, what we look at is the change in the spin vector, so delta psi. And from the change in the spin vector, using those definitions I gave you earlier, we can then find out the change in the spin tensor. And using the definition of the spin vector, we can get delta A. And the way we do that, again, we draw a sum of tree-level diagrams. So what you need to do is you kind of need to just sort of pretend that this dotted line isn't here, and you think about these as all being tree-level diagrams pointing towards the outgoing line, which represents this deflection mode. But when you look at these diagrams, of course, I mean, you would certainly be forgiven for thinking that these are two-loop diagrams. And that's no accident, because if you were thinking about this from an amplitudes point of view, of course, they would be two-loop diagrams. And the real point here is that because modes that live on the world line live in one dimension, whereas modes that live in the bulk live in 4 dimensions, that means that even though we are summing over only tree-level diagrams, we nevertheless end up with some integrals that we still have to do. And you guessed it, the integrals that we're going to end up doing are going to be two-loop integrals. And that was the focus of this paper, which I did with Gustav Jakobsen earlier this year. And we built up this sum of diagrams, and we were able to calculate these scattering observables at third post-Minkowskian order involving a pair of spinning black holes or neutron stars up to quadratic order in spin. But having done that, what we now want to do is we want to go a little bit further, and we want to get more ambitious. And what we specifically ignored in this calculation was radiation reaction effects, which we've heard a lot about today as well. And what we want to now start thinking about is what are the dissipative effects that contribute to this process. So in order to help you understand that, let me now just briefly take an aside and tell you about this Schwinger-Keldysh in formalism. By the way, Michel Levy was also talking about this. It's also referred to as this closed time path formulation, CTP. Basically, the issue is the following. When we normally do quantum field theory in the in-out formalism, we think about an ingoing state and an outgoing state and a transition element, the S matrix, which takes you between them. The difference is when we think about classical physics, if you think about the way you do physics in high school, you have some system which you set up at time t equals 0, and then you just let it evolve forwards into the future. So you fix boundary conditions only in the past. And this distinction becomes important when you start thinking about dissipative effects, because if you have a situation now where your system is, say, leaking energy, there is now an inherent difference between the ingoing states and the outgoing states. You can't just send P to minus P to make this distinction. So in order to bridge this gap, what we have is the in formalism. And what you want to do basically is you have your vacuum state in the past, you evolve it forwards to the measurement point, you measure your field, you evolve back to the past again, and then you have the vacuum. So what you need is 2 copies of your theory for the fact that you have 2 copies of the evolution operator. And while it may look that these two decouple from each other, the 2 fields are in fact entangled to each other through the fact that they satisfy these boundary conditions. Now, when you first look at this formalism, it of course looks horrible. I mean, why on earth would you want to double your theory and have 2 copies of your theory? But the truth is that there's a remarkable, or in fact not that remarkable, simplification which happens here. And this is the fact that if you are focusing on tree level, and if you are looking at one-point functions, then you don't need to actually double your theory. All you need to do is draw diagrams using the exact same Feynman rules, the in-out Feynman rules we had before, but with retarded propagators pointing towards the outgoing line. The reason this has to be the case is because, like I said, when we're thinking about one-point functions, what we're really thinking about is solving the equations of motion. And in a classical context, this is actually not a difficult problem at all. Like I said, you fix your boundary conditions in the past, and you evolve your system forwards into the future. So in the context of the WQFT, if none of that made sense, it really doesn't matter, because all we need to change is one very simple thing. We just take the exact same set of diagrams as we had on the previous slide, but now every single line that we have should be thought of as a retarded propagator pointing towards the outgoing line. And notice that this simplification is only possible because we've chosen to quantize all of the fields in our theories, not just the gravitons. If you were working on the EFT approach and just quantizing the gravitons, this wouldn't work. You would have to double your theory. But because we've quantized everything, we have this enormous simplification, and we can very easily write down an integrand that includes the radiation reaction contributions. But having solved one difficult problem, we've now created a new one for ourselves. And the new problem that we have is the fact that we now have to deal with loop integrals which have retarded propagators instead of the usual Feynman I epsilon propagators that we're more used to. Now, one way we could seek to solve this, of course, is we could try to rewrite them as loop integrals in terms of Feynman I epsilon. But instead, what we're going to do is we're going to do these integrals directly, working in this so-called Keldysh basis. And one thing that you notice very quickly about these integrals is that they are in fact real. If you just simply do a complex conjugation, flip I epsilon to minus I epsilon, and then send L to minus L, you'll learn that actually in the physical region, they are actually real, or rather, they're purely imaginary if you have an odd number of world line propagators. The reason that can happen is you also have to do a Fourier transform to get your observables. And this makes perfect sense, because we are building up a physical observable as a linear combination of these integrals, so it makes sense that we should have this reality condition. But the reason you may not want to tackle these integrals at first glance is because, of course, if you have to keep track of this I epsilon prescription on every one of your propagators, this seems like a terrible idea at first glance, because you're just enormously going to blow up the family of integrals. But it turns out, because we have these delta functions, which also are present, which came about because we have energy conservation on the world line, like I said, they actually serve to restrict the phase space of integration. And it turns out that most of these propagators actually can't go on shell. And the reason they can't go on shell is because over this particular domain of integration, that simply isn't allowed to happen. So what we now start doing is we start distinguishing between what we like to call active and passive propagators, ones which can go on shell, and therefore you have to worry about the I epsilon prescription, and ones which can't, and therefore you don't have to worry about the I epsilon prescription. And in this case, there's actually only one active propagator. At 2 p.m. there aren't any, and that's why those integrals all turn out to be rational functions. So, I mean, the real question then is, given that we know how to do integrals involving Feynman I epsilon, how do we do integrals involving a retarded I epsilon now instead? Well, most of the techniques that we know and love still apply, of course. We can still use integration by parts identities. We can still use differential equations. A couple of things we need to be careful about. The first is that the symmetries of our integrals are going to be modified by the presence of this retarded I epsilon. We need to pay close attention to it when we're doing our integrals. The second issue is that the boundary conditions, when we start fixing our integrals in the static limit, are going to be affected by the fact that we have a different I epsilon prescription. But those are really the only two things that you need to worry about. Now, like other people, including, for example, Zvi, we use this little trick where what we like to do is we think of our delta functions as being a propagator. So that allows us to handle the IBPs in a covariant manner. But the real difficulty here then is, of course, when we have to think about fixing our boundary conditions. And when we fix our boundary conditions, we need to think about the different regions that our loop momenta can enter. And the fact that most of the propagators aren't active is, again, a huge benefit to us, because most of these propagators, because of the restricted domain of integration that we're looking at, they are bound to the potential region. They cannot escape the potential region. So, in this case, we only have to worry about the one propagator which is allowed to go on shell, and that determines the entire, all of the regions of the integration. And there's this lovely little trick that you can think about. If you look at this integral, for instance, it breaks up into the potential and radiation modes, where the potential is, you can think of a diagram looking like this, and the radiation looking like that. The reason this works very hand-wavily, very intuitively, is because in the static limit, you can almost think about identifying the two velocities for these two world lines. So what you basically do is you take the solid line and you move it to the other side. And then you just have to think what happens to this graviton. It can either connect to the other world line, or it can connect back to itself. Those are the two regions. So we build up our observables then. And like I said, we build up delta P, delta psi. From delta psi, we can get the spin kick. And we do now have complete free PM scattering observables involving spinning black holes, including the radiation reaction effects as well. And in order to check this, we do a couple of things. First, we verify cancellation of all the 1 over epsilon poles that we have from dim reg. We also need to make sure that the SUSY charges are conserved. And like I said, conservation of P dot psi guarantees the fact that you're maintaining this spin supplementary condition, which I talked about. One thing that we can obtain from this very quickly, for example, is the radiated Four momentum. We weren't actually the first to obtain this. This was obtained very recently in this paper by Riva, Venezia, and Wong. But I will stress that having the complete observables contains more information than just the radiated form momentum. And for example, then we can also get the radiated energy. And if you know about this bound-to-boundary mapping, then from that you can build up the radiated energy for bound orbit as well. However, this is true just for aligned spins. To give you another example of an observable that we can look at, and indeed which we looked at in our first paper, we can look at the scattering angle. So again, in this case, we just focus on aligned spins. And what we have is we have the scattering angle, which we obtain basically just by taking the mod of delta p. And we look at it in the center of mass frame, and this is the scattering angle which we wrote down in our paper, just for the conservative sector at 3 p.m. So we've got the parts at 0th order in spin, we have the part at linear order in spin, and then we have the part at quadratic order in spin. And I mentioned that we've also been looking at these finite size corrections. So in addition to these S plus and S minuses, which are the sum and differences of the spin on the two bodies, we also have this SE plus and SE minus somewhere maybe. Ah, there it is. Which tell us about these finite size corrections or multipole moments, which we can also have the ability to include inside this theory. But this is only the conservative part. In that paper, what we did is we were able to build up the radiative contribution to the angle by looking at this linear response relationship, which we've already heard of. So we don't need to worry about this term because it starts at g to the 4th. All we need to know is the contribution from radiated angular momentum, which we can obtain, in fact, by looking at the waveform, which I showed you earlier a few slides ago. And if you then look at the complete scattering angle, which you build up as the sum of the conservative and radiative contributions, you then satisfy this very important check which Tibor gave us, which is, of course, we need the entire combination to be finite in this gamma tends to infinity limit. And indeed, now it is, also for the spinning case. Okay. But, of course, this is very nice, but now that we've been able to do the full calculation involving radiation reaction effects, involving the full misaligned spin directions, it begs the question of whether this concept of being able to build up radiative corrections using some kind of a linear response formula like this, whether it can be extended beyond just the simple aligned spin case. And I'm glad to announce Gustav Jakobsen and I have been working on a paper, and we're very nearly done with this. And we have, in fact, now been able to show that there is an extension of Bini and Damour's formula which applies for misaligned spin. And what you want to do is the following. You want to take the formula we had before, and rather now, instead of doing d by d e rad, it's now d by the full p mu, total momentum, and then p mu rad. And then angular momentum, it's d by dl mu, the angular momentum vector, contracted with the radiated angular momentum vector. And this doesn't just work for the scattering angle now. This now works for either the change in momentum or the change in the psi vector. It's the same formula in both cases. Now, one thing that you need to be a little bit concerned about is the fact that, in fact, this formula doesn't give you all of the terms in delta x. As we know, if we think back to the Bini-Damour formula, it doesn't give you the full radiative dynamics. So if you think about the schematic formula, this is just for the aligned spin, this one formula. What you would get is if you knew the conservative part of the scattering angle, you would be able to get the radiative part of the scattering angle. What you would not be able to get is this, which is the radiated form momentum. Similarly, there's a very similar pattern in the spinning case where you can build up the terms which are even in the velocity, but not the terms which are odd in the velocity. This is associated with the fact that what I told you before is that we have two kinds of integrals. We have the ones which are real and the ones which are imaginary when we write them in terms of retarded propagators. The terms that we are able to build up are associated with the terms that are real. The ones that we can't get are associated with the ones that are imaginary. So we get part of the answer, but not all of the answer. Nevertheless, it's still nice to know that there is this extension to Bini-Damour, which works for arbitrary misaligned spin directions. The last thing that I wanted to mention, and the last thing that we've been looking at, is the gravitational potential. So for now, here I'm now specializing back to the case of to the conservative scattering problem. And what we've been able to do, similar to this other group who worked on a very similar problem, we've now been able to build up a conservative two-body Hamiltonian, which describes these two black holes, spinning black holes or neutron stars in the conservative case. And the way that we do that is we simply make an ansatz for it. So we have our Hamiltonian, which is our sum of p squared plus m1 squared, p squared plus m2 squared, and then we have the potential here. And we use this trick, which is that we have this gauge fixing, which involves avoiding terms which involve r dotted with p. So what we, and this was also used at 2 p.m. in this paper by Kosmopoulos and Luna. And the way that so we basically just make a big ansatz for our Hamiltonian, we write it down, and what we then do is we go ahead and we calculate our scattering observables. So we take Hamilton's equations like this. It's purely conservative, so we don't need to worry about including an external source. And we just sit down and we calculate these trajectories of the particles. And by calculating those trajectories, we're then able to get delta P, delta A. Sorry, I should have used the same notation. It's the same thing, the spin cake. And then just simply by doing that matching calculation, we can then fix our coefficients in our Hamiltonian, and then we can figure out what the result is. And I'm glad to say that the result that we obtain matches exactly with this result which we saw earlier this year. The only difference is that we have a few extra terms. So like I said, we've not just been looking at the case of black holes, we've also been looking at the case of spinning neutron stars. So we also have the multiple moments, which have also been included in our Hamiltonian. The other check which we have done on this thing is we've checked against the PN literature. So I'm glad to say that our result agrees with 4PN. That's Levy and Steinhoff. So I think I'm almost exactly on time. So I'll just go through my conclusions now. Hopefully I've persuaded you that this WQFT is a cool thing to be doing. We've built up a whole bunch of new results now in the spinning case. So like I showed you, we've got this gravitational waveform from unbound scattering. From that, we've built up radiative observables like the radiated form momentum, the radiated angular momentum. We've been looking at 3 p.m. observables. We've been exploring this linear response relation, this Bini-Damour formula, looking at how it works for misaligned spins. One thing I didn't get to talk about today was the fact that we've also been looking at tidal effects in the non-spinning case. So we just recently had a paper with this excellent master's student, Benjamin Sauer, where we looked at the 3 p.m. scattering observables involving tidal effects. And there's been a bunch of other recent works on the WQFT that I have not myself been involved in. So there was a paper about the double copy last year. There was this really cool paper about light bending, which came out earlier this year. And finally, there's been some work on WQFT in the context of Yang-Mill, thinking about the I-kernel. I think the next steps for us are fairly natural. We want to go to higher spins, we want to go to higher PM orders, and we also just want to push the technology and try to understand its theoretical underpinnings better, and see what we can do in the context of bound orbits and how this can help with LIGO-type gravitational wave physics. Thanks.
Yeah, thanks a lot to the master of the world line for a great talk and staying on time. Who would like to start with the questions?
Thanks, Gustav, for a very nice talk. Could you go back to the slide where you have this spin supplementary conditions?
Yeah?
Oh, yes, thanks. I was just wondering, so one of the things that I've read from one of Steinhoff's papers is that the spin supplementary conditions actually determine the Poisson bracket structures of spin tensors. And the reason people don't stick to the covariant condition is that the spin supplementary condition, which gives you the Poisson bracket that you shown on the slide, is actually the Newton-Wigner spin supplementary condition. And it seems to be a bit in tension with what you have on the slides. So could you have a Do you have comments on?
I do. I mean, it's a very important point that you're making, and it's actually quite subtle, and you really do need to be very careful with this. You're quite right in saying that this particular choice of spin supplementary condition is not unique. This is the covariant one, and you can indeed make other choices, like this Newton-Wigner. For example, one place where you need to make a difference SSC choice, which I just didn't mention in the interest of time, when you're looking at the gravitational potential, then you want to use what's called a canonical SSC. That turns out to be the most natural choice in that case. So the slightly longer answer here to your question is that this particular choice of the action only has a global form of the n equals 2 SUSY. In the SUSY in the Sky paper, we also wrote down a form of the action which has a local n equals 2 supersymmetry. And the local version of the action gives you the freedom to make different choices of the spin supplementary condition. This version of the action, it only has the global version of the symmetry, so you have p dot psi is the conserved charge. So by specializing to the global version of the theory, you've chosen the covariant spin supplementary condition. The existence of the global supersymmetry maintains it then as a conserved charge. If you wanted to make more general choices, you would then need the local version of the theory, which we had in that paper. I hope that's a good answer.
Okay, then we have one question on Zoom by Riccardo Sturani. Making spins out of quadratic Grassmann variable, don't you get automatically 0 for higher spin interactions?
Yes, definitely. Like I said, I mean, this is only designed to work up to quadratic order in spin. So this is only up to quadrupoles. So absolutely, if you have too many of these Grassmann variables stacked on top of each other, you will just get 0. But because we are only worrying about quadrupoles here, quadratic in spin 1, basically, it's fine. Yeah, we don't have to worry about that. We would, of course, need to modify this theory, and we are modifying this theory in order to go to higher orders in spin.
We could do another short question. Matt?
Hi, so a small technical question about the Keldysh basis. I noticed that it was a bit different on your slides versus Michelle's in terms of the factor of 1/2 being on the term, the plus or the minus term. Is there a way to sort of understand what determines the position of this 1/2?
Do you know, I think I might have just copied it down wrong.
Aha, okay, thank you.
I honestly just can't remember. I think I might have just copied it incorrectly. I don't have a good answer to that. I think it's just conventions.
Okay, then let's thank Gustav again. Yeah, and as a last speaker of this conference, it's my pleasure to announce Julio Paramartinez from Caltech. Please go ahead, Julio.
Thanks a lot, Oliver, and also thanks to the organizers for inviting me to speak here, and thanks to all of you for sticking all the way to the end. We made it. Okay, so I'm going to tell you about this recent work with Cliff Chung and Andreas Helset, both at Caltech, and 2 papers that appeared within the last year, and also some work in progress that should appear at some point with Cliff's student, Maria, who I think some of you might have met at the school. Okay, so just to distinguish my talk from the rest of the talks today, so most of the talks today were about how to use amplitudes to elucidate something about the geometry of space-time, solving the 2-body problem in GR, 3-body problem in the case of Calum. But my talk today is going to be the other way around. We're going to try to use geometry to say something about amplitudes, and actually same kind of geometry that we had in the previous case, just Riemannian geometry. There's not going to be any polytones or anything like that. Okay, and you should rewatch Nathaniel Craig's talk from early this week that introduced some related concepts. Okay, so I'm also going to talk about soft theorems in this context. So just a quick reminder, soft theorems is the statement that the behavior of scattering amplitudes when the momentum of some particle is very small is often universal. So we can make a universal prediction that the soft limit of some n+1 point amplitude is some operation on the n point amplitude. And I guess the earliest example of this, or a very early example of this, is the soft photon theorem by Loberner and Kroll. And here I included also the subleading soft theorem, which is actually a bit older, newer. And there are similar statements for gluons and gravitons, also for scalar particles like pions. There's a famous Adler zero that tell us that soft pion in kernel perturbation theory, the amplitude has to vanish as the momentum of the pion goes to 0. Okay. Okay, so what is the motivation for the rest of my talk? Okay, the motivation is twofold. One is something that always confused me. So there's two kind of a little bit different perspectives on soft theorems. One of them is that soft theorems are a consequence of symmetry, and you'll hear this often. It's either they're a consequence of gauge symmetry for the case of gluons, photons, and gravitons, or maybe a consequence of some non-linearly realized symmetry for the case of scalars. And there's another perspective, which is that soft theorems are just a statement about effective field theory. The fact that very soft particles should decouple and their interactions should be very simple. And an example of this is factorization theorems and things like decoupling of ultrasoft modes in soft collinear effective theory. So I always ask myself, well, which one is it? Is it symmetry, or is it some basic fact about effective field theories? Okay. So there's another perspective that you've heard about having to do with asymptotic symmetries, memory, celestial CFTs, etc., which I will not be discussing here, but you should watch those talks if you're interested in that. Okay, so that's one motivation. The other motivation is that our favorite theories often come with a moduli space of vacua. We have some scalars in our theory, we can give them a vacuum expectation value, and suddenly we have a slightly different theory. A prime example of this is the Coulomb branch of n equals 4 super Yang-Mills, which looks something like this. It's like some cone. There's some radial direction, which is our dilaton. There's some pions that parameterize the angular directions. Here, the origin is the massless theory, what we usually call n equals 4. And this is some theory with W bosons, so some massive particles. And you might ask, how are amplitudes here at the origin related to amplitudes here? Okay, so Mark was complaining yesterday that not a lot of attention has been devoted to computing amplitudes on the Coulomb branch of n equals 4. There's a few papers, but not enough. So today we're going to try to answer this kind of question. But for this, we're going to take a little bit of a detour. So I'm going to describe some aspects about the geometry of scattering amplitudes, then and introduce a soft theorem that will kind of give us some answer to these questions that I posed. Okay, so let's get started. Amplitudes and geometry. This is just a review of what Nathaniel told you earlier this week. So consider a scalar theory. We can organize its Lagrangian in terms of the number of derivatives of each coupling. For instance, the two derivatives can come with a general function of the scalars here, which is symmetric, non-degenerate. And then if you do field redefinitions of this kind without derivatives, these look like changes of coordinates. So you can identify many of these couplings as some kind of tensor in field space that transforms covariantly under field redefinitions, okay? So this is familiar for people who have thought about two-dimensional sigma models, the string with some non-trivial target space, but it's more general. In higher dimensions, the only difference is that this is some AFT, which is not normalizable, okay? Okay, so this Nate already told you about. What about amplitudes? Well, amplitudes are a bit different. Amplitudes are field redefinition invariant, okay? They don't depend on our field basis. They depend on the choice of our vacuum, so some VEV of the scalars, right? But if we do a field redefinition, then the action just changes by something proportional to the equation of motion, which is zero on shell. Okay, so our amplitudes shouldn't depend on this field basis, but they might depend on some choice of frame. So if we ask, amplitudes are overlaps of momentum eigenstates. If we ask, well, how does that talk to a field? There's some field strength normalization, which you can think of as some basis for the tangent space of our field space, okay? And the amplitudes, because they're field redefinition invariant, they actually will be a function of geometric invariance of this geometric space, okay? So I think Nathaniel already mentioned this, but we can look at some example. The simplest example is this two-derivative theory that I showed you earlier. And this is what the 4-point amplitude looks like. Okay, there's many things here. There's 4-point, 5-point, 6-points. You see the 4-point is very simple. It's just a product of Mendelssohn variables and the Riemann curvature of the field space with the components labeled by the flavors of the particles, okay? And I don't know if this is true. Maybe there's an earlier reference, but I think this formula first appeared in a paper by Lance a while ago when they were considering some string amplitudes. Okay, okay, this is more general. There's 5-point amplitudes, unlike in a typical Gmod H sigma model. And there's also higher point amplitudes with factorization channels, everything you would expect. But it's always a function of these geometric invariants. And this makes the field redefinition invariance of the amplitude manifest. Okay? Maybe it obscures other things. For instance, the usual NLSM, you have that the curvature is product of structure constants and that these derivatives of the field strength are 0. So this is not manifest here, but you can plug it in and check that this is correct. Okay. What about non-derivative field redefinitions? Okay, Nate already asked this talk, but there's a very natural thing to do. Instead of considering a VEF of the scalar, we can consider just a background. Okay? And we can upgrade our derivatives with respect to the VEF whenever there were some inner amplitudes to derivatives with respect to this background. Okay? And then you can think of the whole Lagrangian, no matter how many higher dimension operators it has, as a generating function for some object that looks like a metric that will be depending on the scalar, which we can think of as a background, and then the derivatives of this metric, you just take functional derivatives of this metric, which we choose to do in momentum space. And generically, the nth derivative of the metric is literally 1 over p1.p2 times the endpoint Feynman vertex. So it's very simple. But it's nice that you can actually build field redefinition invariant objects off-shell. Okay? So the amplitude is field redefinition invariant, but most off-shell quantities, they're not field redefinition invariant or covariant. But you can build things like the Riemann curvature in this space off-shell, and these transforms nicely under field redefinitions, including derivatives. And in fact, you can do this for any theory. So for the two-derivative theory that I showed you, this reproduces the same invariance that I showed earlier, that just depended on the VEF. But you can do this for a theory with a potential. And then the Riemann curvature looks like this funky non-local function of your momenta plus some function of the backgrounds. So from now on, I'll be just forgetting about the backgrounds and just showing you the 4-point part. For DBI theory, something like this, special Galilean, your favorite theory has something like this, and you can check that these objects satisfy the usual identities that the Riemann curvature satisfies, like the Bianchi identity, they have the right symmetries. And even better, you can just plug this into the amplitude that I show you for the nonlinear sigma model, and you get the correct amplitude. Okay, so there's a general geometric expansion of the amplitudes that manifests field redefinition invariance, sometimes at the expense of other properties like locality. I showed you that the Riemann curvature for a potential theory was extremely non-local, that when you plug it into this formula, you reproduce the correct amplitude for 5 cubed and 5 to the 4th theory. And similarly for the other examples. Okay, so this means that the amplitude, well, a caveat is that the amplitude is only a function of this geometric invariance on shell, but the invariants are field redefinition invariant off shell. Okay, and this goes beyond scalars, so we can do this for any massless boson. For instance, for a gauge field, we have some more complicated metric. Its derivatives look like the usual Feynman vertices. For instance, this is in Feynman gauge. And you can build a curvature just by using the formula for the Riemann curvature in terms of metric. It's some crazy object, it's not gauge invariant, but you plug it into this formula and you recover the usual foreglow amplitude. Okay? So this is making some properties of the amplitude manifest that like field redefinition invariant, that, okay, maybe they're not so interesting for most people in amplitudes, but they're true, and this expansion makes it manifest. Okay? Okay, so that's the background, but if you're an amplitudes person, you should ask me, why do I care about this geometry story? What do I learn about amplitudes, apart from this kind of funky representation of the amplitude that obscures most of the properties that I actually care about? Okay? And the reason is this geometric soft theorem that we found, in my opinion. So the soft theorem intuitively looks like this. This is the actual formula that we will go over, but it tells you that if I take a soft scalar, soft massless scalar in any theory, of scalars, but we also understand how to couple it to other things, as I'll mention at the end. The soft limit looks something like this. It looks like a covariant derivative in this geometric space of the lower point amplitude, plus something which looks like the on-shell emission from the external legs, and essentially this is some sort of an on-shell connection. Okay? This is something that makes sure that taking this derivative typically is not an on-shell operation, since it might take you off the mass shell. So this covariant derivative can hit a mass, but not a momentum. So initially, it wouldn't live invariant the on-shell condition. But this whole combination is a well-defined on-shell operation that you can do on scattering amplitudes. Okay, so we have this derivative with respect to the VEF that essentially adds soft stuff to vertices and internal propagators, and this on-shell connection that adds soft stuff to an external propagator. And this is what the formula actually looks like for a theory of scalars. I just have the covariant derivative with respect to the VEF plus the usual emission, like the singular pieces. This is 1 times this is the leading soft theorem, and this encode the subleading soft theorem. Okay. So let's look at some example. So this is the 5-point amplitude in this 2-derivative theory that appeared in a previous slide. This is also a theory with a lambda d phi to the 4 interaction. And you can check that if we take the momentum 5 of this 5-particle amplitude to 0, then indeed we get this derivative here, which is indeed the covariant derivative of the lower point amplitude. You can also check that all of these terms here, they go to 0 because they all depend on 5, and only the first line is not 0, and indeed it's the derivative along the 5 direction of the 4-point amplitude. Okay. And okay, so these examples are very simple because these were local amplitudes, but if you check this for like 6, 7, 8-point amplitudes with factorization channels, it's actually quite non-trivial to see that this works, but it works. And the proof actually is very simple, though I won't be able to cover it here. So let me make some comments. So this is the precise encoding of intuition that we all have, which is a soft massless scalar should just be a shift of the BEF. So the soft massless scalar should just tell you what the amplitude looks like at a neighboring point in the space of vacua or in field space. Okay. And this is valid for any massless scalar, and it kind of challenges this common law that soft theorems only have to do with symmetry. So this is completely generic. It's just some statement about interactions of very long wavelength particles rather than something special about symmetries. Although there's something else special about symmetries that you can ask me at the end if you're interested. Okay. But for this, there's no symmetry required. Okay. So instead, it tells us that soft scalar theorems, they just move us around the space of vacua. Okay, so we can prove this non-perturbatively, just like the Adler zero for massless theories, and we have a 3-level proof when you have massive stuff interacting with this massless scalar. It encodes both the leading and subleading soft theorem. It generalizes and extends the soft theorems for Golson bosons, like the soft dilaton theorem, the Adler zero. There were also these cool soft theorems that Yaroslav and others discovered a couple years ago for non-symmetric cosets, where the soft pions actually, the soft limit doesn't vanish, but it's a linear combination of amplitudes. So one can prove all of those soft theorems as a corollary of this more general soft theorem. Okay? And it also has a nice interpretation in this context of celestial CFT. It has to do with the space of exactly marginal deformations of the CFT, and it points to another universal sector of operators that have nothing to do with conserved currents. Okay, what about double soft and multi-soft in general? Well, as you might expect, if you take the double soft limit, there's different ways of doing it. But what you discover is that generically this field space has some curvature. And indeed, just by taking the consecutive double soft and taking the anti-commutator, we can measure the curvature of our target space manifold. Or you can take the simultaneous double soft limit, which indeed also depends on the curvature, and it has some extra piece. So this is familiar from double soft pion theorems, where only the first term appears, and instead of the curvature, one has the commutator of 2 broken generators. Okay, and the difference between these two is essentially we're trying to go from some vacuum to some neighboring vacuum along several directions, and there's different paths that you can take in field space to reach the other point. So the anti-commutator is just drawing some like square path, whereas this simultaneous double soft limit is taking some path specified by the momenta in field space. And this also answers this question that I have: how are amplitudes at different points in the moduli space related? Okay, so the statement is that if we can calculate the amplitude at the origin of moduli space, say in n equals 4, with an arbitrary number of soft emissions, that will encode the amplitude at any other point in the moduli space with the full BEV dependence, with masses, et cetera, et cetera. Okay, so we can compute the Taylor expansion of this amplitude in the BEV by just computing additional soft emissions in the massless theory. And there's a known example where this has been put to use, and actually one can resum this series, and there's these couple beautiful papers by Nate, Henriette Elvang, Michael K. Meyer, and others, where they looked at W scattering on the Coulomb range of n equals 4, and indeed they related to soft scalars at the origin of the moduli space. But this is still not completely systematic, so there should be some nice way to use this together with the soft theorems. For instance, we know that in that expansion, typically, most of the time, we're just expanding propagators, and that should be easy to predict. So one should only need a finite number of soft particles to recover the structure, at least at tree level. So I think there's still some work to do here to try to relate, to compute the amplitudes here, just using information here in a fully systematic way. But we can also do the inverse. Whoops. Okay. So there's part of the slide which is missing, but I'll just say it in words. So we can do the opposite, meaning we can also, by knowing the 4-point amplitude at any point in field space, so if we know the full wave dependence of the 4-point amplitude, we can build on-shell recursion relations. So these erase the derivation, but it's very similar to these dispersion relations with additional subtractions that improve the high energy behavior that I guess some authors that were here, but Yaroslav, Cliff, Shashen, Carl, and others derived. So now the idea is that you do recursion, you put something in the denominator, and the residue is exactly the soft limit. So by knowing the full wave dependence of the 4-point amplitude, you can build an arbitrary n-point amplitude at some other point in moduli space. So this is kind of the inverse of this story here. Okay, how much time do I have?
That's another 8 minutes.
Okay, so I think I'm well ahead of schedule. So can we go beyond scalars? Okay, can we take this idea that actually soft theorems, they're just a statement about EFT, they have not much to do with symmetry, and generalize this. And the intuition is that every soft theorem should look something like this. We have some derivative with respect to a background field. We just need it to be constant because we don't care about these derivatives because it's some soft particle. But we'll have to make sure that this operation remains on shell, so we'll have to have some like 3-point vertex, which is sort of the connection, as appeared in Nathaniel's talk. Okay, so for him, they also had this 3-point function, this amputated 3-point function, which was this field space connection. This is exactly what's going on here. And my claim is that, or my conjecture, is that we can rephrase many, if not all, soft theorems exactly in this language. Okay, and we have some evidence for this. So I already told you the story about scalars. So let's look at other examples. For instance, we can ask, what happens with the scalar couples to matter? Then it's not so obvious, but everything works. So for instance, the leading coupling to fermions is this kind of one derivative operator where we couple the derivative of the scalar to the usual vector current of the fermions, and here there's some generic function of the scalar, and the soft theorem does work. The only difference is that now this object here is adding some torsion to our connection that knows about the fermionic directions. So you can check that the soft limit of this, and by the way, this is the work that we are doing with Maria, the soft limit of the amplitude, the soft scalar limit of the amplitude with fermions is still a covariant derivative. One just needs to know about this torsion, which is given by this coupling. And something very similar happens when you couple two gauge bosons. And this is a simpler example, so the general gauge boson coupling is a bit more complicated. But say we have this dipole coupling which couples scalars to fermions and to gauge bosons. You can compute the amplitudes in this theory, and you can check that indeed the 4-point amplitude and the 3-point amplitude, they're just related by this derivative. And you can keep going and check that these kind of soft theorems are satisfied. Okay? And this sort of perspective gives kind of a new viewpoint on well-known things like the Golsan-Boson equivalence theorem. When you try to ask these questions for W scattering, then you find that, well, high-energy W scattering is very similar to W scattering next to some very soft particle, and you can see how this mixes into some longitudinal mode. So it kind of relates to old and well-known ideas, but now we interpret them as some version of a soft theorem. Okay, what about spin? So it also works with spin. So we want to check whether the soft photon theorem is also an instance of this general picture where a soft theorem is just a derivative with respect to backgrounds that encodes that things should change slowly when we couple to long wavelength modes. So this is what the general soft theorem looks like. This is the metric for coupling a scalar to a photon, very similar for a fermion. I told you that this guy here is just the 3-point vertex, just the emission from an external leg, and you can expand it like this. And now this derivative should be the derivative with respect to a background photon. So in principle, that's something complicated to compute. We should compute the amplitude in some constant background and then take a derivative.
But as it turns out, in this case, it's very simple because this background photon always appears together with a derivative. Okay? It always appears inside of a covariant derivative, so we can always trade derivatives with respect to the background by derivatives with respect to momenta. And when you put together these two pieces, indeed you recover the soft photon theorem, both leading and subleading. Okay? So this suggests that this intuition that the soft theorem should always be this kind of covariant derivative might be general. And the extension of these to gluons and gravitons is work in progress. As you might expect, it's a bit more complicated because of their non-abelian nature. Okay, so I think I'm a bit ahead of time, but I'll conclude here. Hopefully I convinced you that the geometry of field space is a useful principle which can be extended beyond simple field redefinitions and provides a geometric expansion of amplitudes that makes field redefinition invariance manifest, sometimes at the expense of other nice properties. It also gives us a new soft theorem for any massless scalar. And there's still an important question that remains, if there's a systematic way to use this soft theorem to move a finite distance in the moduli space. And also I showed you tantalizing hints that there's a general perspective on leading and subleading soft theorems that tell us that the soft theorem is just some derivative with respect to background fields. And the question is, can we use this perspective to find new soft theorems? And I think with that, before finishing, I would like to thank all of you and also Prague and also especially the organizers for putting together this wonderful conference. I've been attending Amplitude since 2015, and this has been my favorite so far. Sorry for the ones that organized it before. There were many, many interesting topics, and we got to visit this wonderful city. So I think we should all give our thanks to the organizers, especially Jara, Carol, all the people that have been working on this. So I think we are very grateful, so thanks a lot. Yeah.
Okay, before I join in thanking the organizers, maybe we should have a brief discussion of this wonderful unification of geometry and amplitudes. Any questions to Julio? Shruti, please.
Thanks for the nice talk. I was wondering if you've thought at all about fermions and if you get some kind of metric on a supersymmetric manifold or something like that.
Yeah, so there's a naive thing that one can do, which is just add fermions that are in some multiplet with the scalars, and everything works as expected because essentially you just have one geometry. I think the more interesting question is what happens when you have some fermions that are not related to the scalars in any way, and whether there is a general soft fermion theorem. Okay? So we know there's only one instance that we know of a soft fermion theorem, and that's the soft Golsino theorem, and that one follows from symmetry. That's when you have spontaneously broken supersymmetry, like Polkov-Vakulov theory, something like that. But this suggests that maybe there's some more general soft fermion theorems that don't rely on a spontaneously broken symmetry. So I think that's a very interesting question, but I don't know the answer. Yeah.
Yeah, I see two further questions. Maybe. Yep. Please.
Yeah, thanks for a nice talk, Julio. Just a question about simultaneous double soft theorem. I know, as you know, the consecutive double soft has a clear symmetry interpretation in the standard sense, and the simultaneous double soft seems to be no universal, right? Is it clear from your perspective? Does your perspective offer a new interpretation, like kind of the simultaneous double soft theorem?
You mean in the case of You mean in the case of gluons and gravitons that it's a bit more subtle, or when you say that it's not universal?
Well, yeah, exactly. So I mean, usually it's a commutator of charges when you compute the consecutive double soft, so it has a clear symmetry interpretation, at least for, well, from a asymptotic charge point of view. But it seems like it's very no universal, like in the other case, like it's probing some kind of interaction. So from your expression, I see that there was some symmetrization on the covariant derivative.
That's right. So the kind of more universal part is this part that knows about the commutator of charges / curvature, right? But there's also this piece that tells you that you're just moving in the moduli space, and if you're doing the Taylor expansion to second order, you should expect the second derivative of the amplitude to appear. Okay, so indeed there's this extra term, but in this case it's universal. Like we know what it is, and one could ask what happens in the case of photons and gravitons. Can we interpret the mismatch as this sort of derivative? That's a very interesting question. Yeah.
Thanks.
I saw further raised hands.
Thank you for the nice talk. This looks like an interesting way to probe soft theorems. Do you think there's any scope for extending it beyond flat space? So, for example, to look at soft theorems on like fixed curve backgrounds?
Well, in fact, if you ask the people who work on cosmological correlators and wave function of the universe, these kind of things, they've been doing this sort of thing for a while. So, for instance, there's these consistency conditions on inflationary correlators that people have written, and they're essentially a soft theorem, and the way they derived them was by thinking about some slowly varying background. So indeed, this is a very general story. I've applied it to amplitudes, but one can take one step back and ask, what are these statements about correlation functions? And I believe many of these things should carry over to these setups. And in fact, I know for a fact that people have been doing this for a while. Yeah.
Thank you. Let's have a last short question from David.
Curious to know whether you think that there might be some similar extension to other universal factorizations like collinear factorization.
Well, yeah, I haven't thought about this, but a soft theorem, well, collinear factorization does rely on the fact that there's something going on shell somewhere, but I don't have an intuition of it as probing some long wavelength mode. So from that perspective, maybe it cannot be put into this framework, but maybe someone has a different intuition about collinear limits and can show that this is wrong. But I would expect that soft limits can be phrased in this language, but not collinear limits. Yeah.
Okay, then let's close this talk. Thanks again to Julio. And let's most of all give a gigantic applause to all the organizers for this really wonderful conference.
Thank you. Thank you very much. We will have a traditional ending with the final distinguished speaker. And before that, let me thank in person people who were helping us with organizing this meeting. Let me start with agency AMCA, represented by Eva Uhrova, the lady who was sitting behind the desk, or Martin Karliček, who is sitting here. Let me continue with our younger colleagues helping us with the microphone, Taro, Petr, Christoph, David, I hope he's still Michal. Of course, we have to help also people who are not that visible, or institutes who are not that visible, like our home Institute of Particle and Nuclear Physics. I'm happy that other institutes are still represented by a living person. So let me start with Seiko Institute of Physics, represented by Martin Schnabel here, and Will Emond and Renan. I hope they are still in the room. Let me thank also the Mauming Institute, represented by its director, Byrne here, and very generous ERC grant contribution by Johannes Henn. Oh, let's see if I haven't forgotten anything. Masaryk University is represented by Klaus Behring, of course, sorry. This was the reason I wrote it down. Last but not least, I would like to thank Aynan, saving my computer. He was that fast, my computer was sliding down, and he jumped and saved me it, so thank you very much. And as I said, we will have still 2 talks, so let me start with the first
talks.
one.
Okay, thank you. So just a few concluding remarks. So in the beginning, I promised to collect slides of future meetings to put on the calendar. We already heard about it during other talks, but let me review all of them. It's the program next summer in Nordita. It's the summer school, South American summer school on Amplitudes in Brazil. It's the QCD meets gravity this December in Zurich. And it's, of course, the next year Amplitudes conference and the summer school at CERN. So there is a long calendar of things you should put on your personal Google Calendar. And also, we are planning to organize with NEMA another GeoAmplitudes, which will be online meetings, so watch for announcements for that. Then the next thing, I was gathering some data during the week on the winner of the Amplitudes Olympics, the participant with the biggest number of points. Sorry. So before that, I would like to remind you that our webpage will be updated gradually with talk slides, and also our YouTube channel with talks for this conference and also the previous summer school. Okay, so now let's go back to the winner of the Amplitudes Olympiad. So we have 3 winners with the gold medal, which participated in 11 of 12 in-person conferences, which is Johannes Henn, Henrik Johansson, and Gabriel Travaglini. So I think they deserve applause. And then we have another set of the silver medal, including Lance, Einan, and myself. Bronze medal by David, Livia, Simon, and Ruth. And we have honorable mention also with people with 8 participation. Perhaps this list is incomplete, so if you were offended by not being here, despite participating in 8 and more conferences, let me know, and I will, of course, update it. Okay, so it was a pleasure to host you all of you in Prague. I hope you enjoyed the week. And the final few words will be by our very own Lance Dixon, but sorry, wait a bit, Lance. Maybe not all of you know, I hope most of you know, that, what happened? Of course. Okay. Maybe not all of you know that earlier this year, Lance was inducted to the National Academy of Sciences. It's one of the biggest recognitions for the American scientists. And we are all very proud of Lance. He's very best of us. Congratulations. And Lance also made a significant mark on these 2 weeks. He gave a set of beautiful lectures during the summer school. He told us about his fascinating discovery of antipodal duality during the conference. And if you haven't seen the latest Quantum magazine on this topic, I strongly suggest to check it out. I hope Lance also enjoyed Prague as a city. We had some nice walks around the town and some fun. And yeah, thanks a lot, Lance, for coming to Prague, and special thanks to Růžena Veseláková for bringing you in. Okay, thank you. Lance.
Well, thanks for those very kind words, Yara. Now you might ask, what am I doing up here? And well, basically, Yara seemed to think I might give the after-dinner speech, but fortunately for you, and also for me, that didn't happen because of the venue. So, but he forced me to give a few words now, so I told him he would be sorry, but he insisted. So I think, like everyone else, I thought this was just a fantastic Amplitudes, and not just for the setting, but the ability to interact with everybody after a few years away. I think I sort of got stuck with this job because I kind of gave closing remarks in these Zoomplitudes we had for the last 2 years. But anyway, you know, when you get to do things in person, you make surprising discoveries that you often can't do over Zoom. And anyway, it's so great to be back together again. But one of the discoveries I made was another duality. But to explain this duality, some of you don't really know this person. His name is Yara Zimmerman. And he is the most famous Czech who never lived. So as Carol explained to me one time, when Alexander Graham Bell invented the telephone, he picked it up and he discovered that he had 3 messages waiting from Yara Zimmerman. And I think Yara Zimmerman was also an intrepid explorer of the Arctic. He ran away from some cannibal tribes and he missed the North Pole by just 7 meters. Anyway, with all that background, you can understand, I think, by now that Yara is dual to, Yara Trinka is dual to Yara Zimmerman. It's just so obvious. I mean, it says up here, Czech polymath. That's clearly just short for polytopal math or polyhedral math. He's a multifaceted scholar, rumored to have invented the amplituhedron, some people say. He's also an outstanding photographer. I think I have to stop wearing my Stanford MAGA hat now. It's too red, but, okay. And a conference and school organizer, and how he could organize both and also lecture, and gave incredibly clear lectures. I got to see the reviews. Not everybody's seen the reviews, but he did very well. He's also an amateur genealogist. I kind of emphasize amateur, but okay. So anyway, that's one duality. But there's yet another duality. This here is Carol the Fourth. Can anybody guess, you know, who he's dual to? That's right. It's Carol Camp. And as you can see here, he is the discoverer of the quadruple copy. You know, if Einstein is Yang-Mills squared, the double copy, Carol discovered the quadruple copy. Now, I want to say I was right there when it happened, but it's really all Carol. So, also, of course, a fantastic conference and school organizer, as well as tour guide. He gave lots of great tours and introductions to Prague to everyone. So, and he also knows the meaning of candle sauce. And if you don't know, you'll have to ask him. So thanks again, and thanks to everyone else who gave us such a wonderful conference. But this wouldn't quite be complete if we didn't give the last word to Greta Thunberg. If you don't know, she was present at the end of the last 2 Amplitudes conferences too, where we all behaved very well and did not travel to the conference venue. But this year, she knows that some of us flew to Amplitudes. Okay, so please take the boat back. So, safe travels, everyone, and see you guys next year. It's a busy summer, so get to work writing those papers. Thanks a lot.
Okay, it's over, and we will still have coffee outside until 4. They actually moved the coffee